Hi, my name is Craig Gardner. I'm a technical training architect at SUSE, and in addition to that role that I play within SUSE, I am also a member of the Open HPC Technical Steering Committee. I'm happy to be a part of this presentation together with my friend and colleague Alessandro Festa. It's interesting that he and I have been working together on this, particularly because of what I will certainly come to show you in the following slides, the differing roles that he and I play. When Alessandro and I originally planned to give this presentation at SUSECON, this was going to be a hands-on demonstration, an opportunity for those attending SUSECON to have the actual experience of going through what it is that I will demonstrate here. As we have transitioned SUSECON to a digital conference, this now ends up being merely a demonstration, but I hope to present it in such a way that you can see what it is that I'm doing and then perhaps put it into practice in your own demonstration, your own non-production environment to get some experience doing it. Most importantly, our demonstration here today is intended to show you how the artificial intelligence and machine learning efforts and activities and technologies can be enhanced with the deployment of and the use of high-performance computing. Nothing goes together so well as machine learning and high-performance computing. In a machine learning and an artificial intelligence environment, you have huge demands for computing resources. You're going to be doing lots of computations. You're going to be doing computations that are going to result in the rendering and some graphical data represented and rendered in such a way that you're representing large quantities of data in a comprehensive way that people can make sense of. And that often requires large quantities of computed data. And that's where high-performance computing is such a help for the machine learning and artificial intelligence environment. You've got there at your fingertips all of the computing resources of a high-performance computing environment. This is a great marriage. I'm sure that all the data scientists in the world can see the benefits of this, but that might be a little bit intimidated by the fact that if I'm going to enter into a high-performance computing environment, I now have greater demands for skills that a data scientist might not necessarily have. Moreover, from the other side of that, you have all of the high-performance computing specialists, the people that are system administrators or DevOps experts who have all of this knowledge and all of this expertise and all of this hardware, all of this machinery, all of these compute cycles, all of these CPUs and GPUs that have resources available, but that aren't sure how to make them better available to those data scientists who would make use of them. So in this demonstration and together with the solutions that SUSE has proposed to provide in the coming months and days, back up, say that differently. I want to make sure that we fix that in the recording. That SUSE has coming in the days and months ahead. This marriage will become all the more obvious. Will become all the more useful and all the more productive. In this demonstration, we hope to accomplish the following objectives. As a listing of things that we hope to accomplish, I also want to make clear something that we will not accomplish. We certainly can't make you data scientists. Most people that would be attending SUSECON would be more of the systems experts, more of the technical experts, and not necessarily the data scientists. And we would not necessarily expect data scientists to be attending a technical conference such as SUSECON, even if it's the digital SUSECON. If there are data scientists who are listening to this presentation, I welcome you, and I hope it's useful and meaningful to you, and I hope that I don't misrepresent anything, and I hope I don't embarrass myself by saying stuff that I shouldn't be saying, because I am not a data scientist. But I at least have the hope that through this demonstration, through this recording, that I can expose you to a variety of the industry standards and the movement that's behind artificial intelligence and machine learning. I will certainly give you some interesting experience with HPC and how that will benefit the efforts of artificial intelligence and machine learning. And most importantly, I hope that through giving that an interesting experience, that it becomes less intimidating for those of us who are more on the technical side of providing resources, that we can see that providing an HPC environment can enhance the experience of data scientists, and that it shouldn't be something that drives either of these lanes of expertise away, that they can be brought closer together, that they can be mutually beneficial to one another in providing good solutions for crunching numbers and the data science that's behind that. Lastly, one of our objectives in providing this demonstration is to give a little bit of a glimpse into what SUSE can do for an enterprise that needs to have good data science and that has the means to provide a high performance computing environment, and bringing those two together in a way that makes sense and that is useful. Our agenda for this demonstration can be broken down into these 5 steps. First, I'm going to provide a short introduction beyond what it is that I have already given by way of introduction. Then I will show, not exhaustively, but at least in a representative way, the basics of setting up a SUSE HPC environment. I'm going to do that in an AWS Cloud. Now, that's not an ideal circumstance, but it's certainly a functional one. Following the setup of HPC, I'm going to demonstrate some of the very simplistic uses of MPICH, which is a specific implementation of MPI, and to show that you can use MPICH for distributed workloads within a high-performance computing environment. After showing how MPICH works, then I will set up a Jupyter Hub in the HPC cloud that I have created. And then the last thing that we will accomplish is to scale the Jupyter Notebook workloads, make the notebook aware of the HPC resources, and therefore to scale out the work that a notebook must do amongst the variety of compute nodes in the high-performance computing cluster. By way of further introduction, let me just bring to your remembrance some of these things that I alluded to earlier in this recording. Sometimes we can see a conflict brewing in the enterprise as it relates to the objectives of those people who are responsible for the infrastructure and the compute resources in the organization. You have the DevOps folks, you have your system administrators who know their systems and they know the infrastructure, and they have not rigid, but they have measurable responsibilities for how they are accountable for how the systems are to be used and how the infrastructure is supposed to operate and the reliability of all of this infrastructure. And generally speaking, they know absolutely nothing about data science. And I hope I don't offend anybody by saying that. I'm certainly in this boat here. I am the DevOps expert, and up until I've been working on these kinds of projects at SUSE, I knew very little about the data science. More to the point, I don't know that anybody can be an absolute expert in both, and nor should there be an expectation that there be that depth and breadth of expertise in both. On the other side of the coin, you have data scientists who know everything there is to know about their data, about the models, and about their tools, but they know only enough about the systems and the infrastructure to be dangerous. And there's very little trust between these two camps. Again, I'm not trying to trivialize the expertise that some people may have. As a generalization, this is true. And the DevOps folks don't like what the data scientists are proposing or expect to do with the resources, and the data scientists wish that the DevOps people could see what it is that they're trying to do and understand, and they're not trying to be malicious and harmful, and yet there is difficulty, there is conflict in trying to accomplish their varying objectives. What we try to do and what we intend to do, what we want to do at SUSE is to help the enterprise to narrow the gap between these two organizations, to reduce the headaches and the misunderstandings that come from the DevOps side, and to provide an easy environment, a functional environment for the data scientists without them having to meddle too much in the system administration side of things. Now, bear in mind that for this demonstration, which is necessarily brief and is necessarily not exhaustive, there are far, far more details that we could discuss in both of these camps. There is a lot that I could talk about to teach you about all of the characteristics of and the individual components of a high-performance computing cluster. And there are so many details that could be covered, although not necessarily by me, but by someone else who is a data scientist character, who could teach you about artificial intelligence, machine learning, modeling, the computational science between all of it. Both of these fields are far bigger than can be fully demonstrated, and then I will have time to be able to demonstrate in this recording. This demo is just a glimpse into each of these, and particularly into how they are the perfect marriage one for another, and why SUSE wants to be your solution provider in bringing these two important fields together. I've already spoken enough. There's a little bit of the slide material that has led up to this, and I don't intend to provide any more slides for the remainder of this presentation, other than for the major sections to provide the information that will lead into the demonstration. Generally, from here on out, I'm just going to provide for you a screen share of the web page or the terminal session that I am using that is involved in these particular sections, the activities associated with these sections. And the first of these activities is to set up the SUSE HPC environment. I mentioned that we will do this in an AWS Cloud. Running an HPC environment in a cloud, whether it's Amazon or your own private cloud or OpenStack cloud, whatever the cloud is not ideal, but it's certainly functional. You're certainly capable of doing that. You won't experience the best performance that a high-performance computing cluster would expect to experience, and so you have some overhead that's associated with that. Plus, you have the lease time and the cost that's associated with that in terms of the quantity of the compute cycles and the quantity of CPUs or GPUs that you have within that cloud environment. It's interesting to note that that in certain clouds, such as AWS, you can actually emulate the GPU capabilities as well. You have GPUs available if your high-performance computing demands or would benefit by GPU calculations rather than standard CPU calculations. Nevertheless, even if you recognize those limitations, or not necessarily limitations, but the operating environment that is presented to you by the cloud and the expense that may be associated with that, it's certainly feasible, it's certainly possible, it's technically conceivable to run a high-performance computing environment within a cloud. We've chosen to do this for the demonstration simply because it's easy. It's very easy to set up and tear down the environment for demonstration purposes. In this particular demonstration, I have 5 systems running. I have 5 instances of SUSE Linux Enterprise Server version 15 with Service Pack 1 running in the space that I have allocated. One of those servers is going to be the HPC head node, and then the other 4 are compute nodes. So to a certain extent, you're going to have to take for granted that we've set all of this stuff up, and I'm not going to show you exactly how you might do. There are lots of ways that you could do that. You could use the HPC mechanism known as Werewolf as an option, as a possibility for setting up all of your servers, your compute nodes within your HPC cluster. You could use more SUSE-oriented standard tools like AutoYast, which is an easy thing to do. And there are certainly a variety of other options that you have to set up your HPC environment, the base systems that would be used. In this particular example, simply because it was easy to do and this is simply a demonstration, I only allocated instances from community provided images that are out there. It was just simple to do. And in a cloud environment, that really is a very simple way of doing it. But there are a variety of ways that you could do it that might be very different in your environment, and that might be necessary to do to follow your company policies or your way of doing things in your shop. After I have a base operating system installed for these 5 nodes, then we need to install the high performance computing module from SUSE, the SUSE HPC module for SUSE Linux Enterprise Server. It's simply a module. It's an easy thing to do. I will demonstrate how that's done. After installing the module and the necessary software that goes along with HPC for these different roles, one role for the head node, and then a separate compute node role for the 4 compute nodes, then we need to set up what may be a very common high-performance computing environment for users. And this is certainly not the only way that it is done, but this is a very common way that it is done. Users are typically managed with NIS, and then the disk that is used for the home users, the home storage space for users, for standard users, might be readily made available by way of NFS. Again, there are lots of ways that you could do this. As a matter of fact, SUSE Enterprise Storage is an ideal way of doing this. But just for convenience sake and for simplicity, so I'm not trying to complicate this demonstration any more than it needs to be, we'll use NFS. And again, NFS is a widely used solution for that. Once we have NIS and NFS set up, then I will create a data scientist user. We'll call this user the scientist user, and then show that scientist now has his home directory readily available all throughout the high performance computing, the HPC cluster. And that would be a standard approach to having data scientists being able to access an environment where they could do all of their machine learning, artificial intelligence, in an HPC environment. Here we see the AWS console where my demonstration servers are running. I have 5 nodes that are represented here in this list. You'll see that I have 4 nodes that are represented here by the name of AIML HPC C1, C2, C3, and C4. Those are the compute nodes, the 4 separate compute nodes. And then I have a node here named head 2. The 4 compute nodes are significantly larger resources within the cloud. My head node does not need to be a big, beefy server. The compute nodes need to have more CPU and more RAM, and so they have larger instances that have been allocated in the cloud. If we take a look at one of these, this isn't going to tell us a whole lot more about this particular server. We'll have to see more about that as we look at the command line and shelling into this particular compute node. But you can see some of the details here about this node. You particularly can see that I just used one of the standard community provided images to spin up this particular machine. And that this machine is indeed a SUSE Linux Enterprise Server HPC-oriented instance, and it comes from SLES 15 SP1. And it's a BYOS. I'm going to go ahead and provide for it my own license so that I can get everything appropriately installed for it. Now, everything that you see is, of course, just going to be temporary. If I happen to give away any particular secrets here, just know that this is ephemeral in nature and it's going to all disappear sooner rather than later anyway. But I do intend to try to obfuscate any information that could make it easy to hack and cause all sorts of challenging circumstances that we want to avoid. Let's see, let me click also then here on head 2. You can see that it is all made up of the exact same resources and it came from the same image is what I'm trying to say. It has a smaller number of resources. It has less RAM and less CPU, but all comes from the same source of image, and it has the same SUSE Linux Enterprise Server 15 SP1 installed on it. Now this is just the compute nodes and the head node in a real HPC environment, particularly for one that's going to be providing more comprehensive services in an enterprise environment. I would have a lot more of this. There might be multiple heads. There would certainly be more compute nodes. And in particular, what I want to point out here is that there's no NFS server here, no redundant NFS services that are running here in this small demonstration environment. The head node, I'll scroll down here, has 2 disks, 2 block devices that are attached. The root device is the operating system, but then I have this dev SDN block device, which is going to provide the NFS, the file system that will be available for common use of all of the compute nodes. Typically in a real HPC environment, you would have a separate large disk farm or appropriately sized disk farm with servers that are going to be providing that service. We're just emulating that here from the head node in this demo. One last thing that's probably worth mentioning here is this is an Amazon Web Services cloud. And for me to get things to communicate all together correctly, all of these resources need to belong to, let's see, I think I've got that. Yeah, here we go. You can see the security group. I have created a single security group that each of the different servers belong to collectively. So I've called this the Artificial Intelligence Machine Learning HPC security group. And they all have the same security settings. And let me just show you that. This is one of the most difficult aspects of running HPC and these machine learning activities within a cloud is getting all of the ports appropriately opened, that the machines within the cluster can communicate together. So I'll click on the security group here, and your experience may be different, but in general, this is what I had to do for getting ready for this demonstration. You see, I had to be very meticulous about opening ports. I can't even get NIS to work correctly unless I give access to the NIS port and the ranges associated with that. To get NFS to work, I have to have specific ports open. And to get things such as slurm and mpitch to work correctly, I have to open a bunch of different ports. I'll explain a little bit more about this range right here that you can see for the custom range for mpitch when I get later in the demo. You'll have to tell mpitch to use a specific set of ports. If you don't, then it's just going to come up with a randomly generated set of ports and try to communicate among the compute nodes with the head node with those random ports. And that can definitely end up causing you problems if you don't have those ports open. So I've got a very limited range of ports open here in AWS. I have to tell mpitch later to use that, only that range of ports. Anyway, you can see the level of detail that you have to get into trying to run this in this kind of a controlled environment. It's not necessarily, I'm not saying that it's bad, I'm just saying that that's one of the things you have to worry about. Now, having looked briefly at this view of the instances within AWS, let's go ahead and connect with SSH and show a little bit about the setup of the individual machines within the cluster, the setup of the individual machines within the cluster from the system side. To begin to demonstrate here that we've got everything set up for our HPC instantiation process here, we'll just show that there are a variety of things that we don't have yet. And let's start then just by talking about name resolution. In an HPC environment, you would likely have a DNS server, and your DNS server would provide host names for all of the machines in your cluster. I could certainly do that, but that's really beyond the scope of what it is that we want to demonstrate here in this demonstration. Just bear in mind that for HPC to work in a way that is meaningful for an enterprise, and particularly with a complex and a high number of compute resources that would exist in HPC, you would likely want to have DNS. So in this particular environment, I'm not going to set up DNS. I'm just going to use a simple hosts file. So here I am logged in. You can see I am connected right now to the head node of my cluster. And in my cluster here, I have this network that I have dedicated for my cluster. It's a very small network. It's just a CIDR mask of 24 for 254 hosts within this particular network. And that's plenty because I've just got the 5 machines. And because this is running in AWS, I've just got it so that it is automatically assigning the IP addresses for the nodes in my cluster. So they're all going to have something 10.0.10 dot and then a node number. In this case, the head node has the node address of 81. To set up my host file for name resolution, I will cat the hosts file here, and you can see that I have the host's IP address and their associated host's name just appended to the bottom of my hosts file. So these are all of the IP addresses that have been assigned by AWS. In your enterprise environment, that assignment may happen by some other way. And you could certainly use some other mechanism for this, whether you wanted to use DNS mask or all-out more powerful bind mechanism. Whatever it is that you use, make sure that you've got these hosts represented. And then I would copy this host file, since I'm only using a host file, to each of these hosts so that each of them has a copy of the host file, that they will know who each other is in the network. Once I've got that, I should then be able to ping compute 1. And indeed, I can ping compute 1, and it's giving me responses there. I could ping 2 and 3 and 4. So all of my compute nodes are running. That's an important step. It could be more complicated for you. In this demo, we've simply used the host file and got all of the names resolved by way of the host file. We need also to have time service running well. There are other softwares that require very, very tight time synchronization. SUSE Enterprise Storage is one of those products that needs to have really good time synchronization. And HPC doesn't have to have that high level of time synchronization, but it does need to be pretty well in sync. So just because it's easy to do, I'm going to just show you how to configure cronny and get that working as a time source. So let's go ahead and edit etc cronny.conf. And in this file, obviously you can do this from YAST as well. But the very simple thing to do here with cronny, as you could with NTP in times past, is to set this up as a time service. And first of all, we'll need to change this value here to allow NTP client access from the local network. So we'll go ahead and copy that line. I'm using VI, so I used a yank place YP to put that on the next line, and I'll get rid of the comment by pressing X. And then I need to change this to the appropriate network where its time will be served. So we'll just change this whole word because we need to change the whole thing to 10.0.10.0, and we're on the 24 network. But there is one more thing that you have to do in order to allow this particular server to act as a time service. And you need to change this line right here, local stratum 10, remove the comment on that particular line. Now, obviously, there are far more comprehensive ways of doing this. In a more enterprise environment, you would have a time server, and you might want to point everything in your cluster to that one or multiple time servers. Having a redundant time service is even more important. It would be more characteristic of an enterprise environment. But for this simple experiment and demonstration, these are the only things that we need to fix here to make this particular head node the time server. So we'll go ahead and write and quit out of this particular file. We'll run system control and show that cronny.d.conf, service is what I really want, is running because it is getting time from the AWS server. You can see that AWS time source is listed right there. But we need to change our configuration to act as a time server. And so we'll just restart cronny D by changing status to restart. And let's take a look then again at the status. And we're now set up to be a time server for the other machines that are in the cluster. Now, since I have a host file, then I can just shell into AIML HPC-C1. And on this machine here, I can edit cronny.conf and now tell it to have our source listed here in this list of servers. So of course it could get its time service from the pool, like as the default value here for pool.ntp.org, and we can also add then 10.0. Let's do it by host name, since we have a host file, AIML HPC-head, and we'll save that now. That's really all we need to do for cronny to work here. System control restart, and cronny d.service. And now we can use cronny c. Oh, and I forget what the argument is that we pass to it to show us what the status is. It's not clients, it's like server. Where is that? Must be up here at the top. Sources, that's what it is. I quickly forgot. So we'll just type sources here, and you can see that we're getting time service served by the cronny service there. So we'll quit out of that. Actually, it's not currently being served. Let's just see if it takes a moment to synchronize sources. Well, let me quickly troubleshoot that and figure out what's going on there. Okay, I cleared the screen there and fixed the problem. The problem was really a simple one, in that was one of the ports that I had not set up correctly in AWS to allow traffic through. So once I went back into the security group in the AWS control panel and allowed port 123, then it was allowing the time synchronization to go through. So in the process of my troubleshooting that, I also removed that local time source of the 169 address from the configuration file. So actually, let me just show you again here. The cronny.conf file. I removed this here from the top line, plus down at the bottom of the file there was a server line down here that had that exact same IP address for the local, for the 169 address, not for the pool for ntp.org. So I removed that server address from the configuration file, and then as I run cronny c sources, you can see now that the head node is indeed attached and serving time connected to my compute node. Good, now I have time service set up for the first compute node. I won't go through all of the process of doing the same in the recording here to all of the other compute nodes, but you would need to do that on all of the different servers within the cluster. Clearly, there are easier ways to do this. For a cluster of 4 compute nodes, no big deal, my going in and adjusting all of these settings. There are other ways of doing this that are much easier to accomplish with standard tools. If you were using just standard HPC, you could use Werewolf to set up this kind of thing. If you are more SUSE-minded and like to use other things like YAST to set up the time services for each of the different instances of the compute nodes within your cluster, you could certainly do that. And there are other SUSE tools that would be similarly useful. If you wanted to use Salt, you could do that. That's not a SUSE tool, but that's something that's very common within a variety of SUSE solutions. Or you might even want to use SUSE Manager. SUSE Manager would be a tremendously easy and comprehensive way of managing all of your deployment of servers and services within your cluster if you wanted to use something like that. Needless to say, there are a bunch of choices. I've chosen a very simple one of manually editing this simply because it's a demonstration and I have a small number of nodes in the cluster. So with that, let's see, I just will clear the screen and we'll move on to the name and we'll move on to the next. To get our HPC cluster configured now, we need to get the software installed and the channels set up. I'm still connected here to the compute 1 node in the cluster, and I'll just show you here SUSE connect dash let's see, list. What is that? List. I don't remember. No, list is good enough. That would show us the extensions. That's right. If I used list extensions, I think is the full argument that you need to have here. You'll see that I don't have anything connected. So I don't have a product, I don't have a registered product, and so I don't have access to all of the pools and such. If I look at etc zip repos, I don't have any repos for this particular compute node. So none of my machines, none of the compute nodes, and not the head node have anything set up beyond the base operating system that came with the image that I had in AWS. Now, there are a variety of ways that you can do this. Again, you could set up all of this with something like YAST. You could use SUSE Manager to have a set of repos and to do your registration to your SUSE Manager server for your cluster. You could use RMT. You can even use the older SMT, although that's no longer a supported product, but that's certainly a viable way of doing it if that's how you have things in your environment and that's something that you're comfortable with. In this particular instance, I'm just going to use the standard SCC, the SUSE Customer Center, and do a registration here with this command. Now, I'm not going to show you what my registration code is because that would be giving away things that would not want to do. But using exactly this command and providing my registration code and you providing your registration code, I could now register all of the nodes in my cluster to have the appropriate software installed. So I'm going to stop the recording and going to run that SUSE Connect with an appropriate registration code, but not let you see it because I don't want to give that away to you. That would not be a good thing for me to do. And then I'll restart the recording after I have completed the registration. And so we have fast forwarded through time here. You can see the end of the output that has taken place here during the registration process with SUSE Connect. And my system has been registered entirely. So now I can show a listing. Whoops, I have to be on the right context here. I can show the list extensions that I have installed on this particular host in my cluster. And down here at the bottom of the list, there's more that has scrolled off of the screen. But at the bottom of my listing, you'll see that I have the HPC module installed on my cluster machine, my compute node. Now, I've only done this in this demonstration for this one host. I would need to do this on the compute nodes, and I also need to do this on the head node. And there, again, are a variety of different ways that I could do this. I even have something suggested here down at the bottom where they're using RMT and SMT or SUSE Manager or a variety of other ways. But whatever it is that's necessary for you to get the software installed so that you can take full advantage of the SUSE HPC module would be appropriate. And of course, not just the SUSE HPC module, but as part of registration, making sure that you have SUSE Linux Enterprise Server also registered so that you can get the software updates and the security updates, all of those important updates for the machines in your cluster. Having completed this then for cluster 1, for compute node 1, I'm just going to break away from the recording and perform the same task on all of the other nodes in the cluster, and then we'll come back here in the recording to the next step. In this step, we're going to show that we've got the repositories available and then begin installing the software. Now, I've gone through the registration process on all of the 5 nodes in the cluster, so they all have access to the repositories in being made available by my SMT server, or by SUSE Manager, or by the customer care center, the SUSE Customer Center. Regardless of what your source is, I've got them all registered. So now let's go ahead and just show zipper list repos, and no reason to show the URLs. That you can see all of the repositories that are now available to this node. We can also look at that here in etc zip repos, just as there's represented as files. Having done that, then let's have a look at what software is available and what's going to be specifically important for the nodes and their roles in my cluster. I'll clear the screen, and here we'll just use the zipper command again. Of course, you can use yast to do this, but I'm a sysadmin kind of guy, so I'm going to use the command line here. But we'll use zipper search. We'll search for patterns, and we'll just see what patterns are available for the registration that I have. And I've got a few patterns available. Some of them are more interesting than others. I don't want to install a LAMP server or a mail server. What I'm looking for here are these HPC strings. And this is a compute node. I'm still here on compute node 1. And so I want to install the compute node pattern and the libraries pattern. I certainly could involve the development node pattern if I were going to be doing development here, and in a different circumstance for a different demo, that would be something interesting to do, but I'm not going to do that here for this demo. And of course, there are all of the other different patterns that I could install if I really wanted to, but in my high performance computing cluster, I want to be very precise. I want to be very deliberate. I want to be slim and trim without any bulk or bloat on these nodes. So I just want to install only what's necessary. So zipper install, and I'm going to use type pattern again, and I'm going to install these two patterns, the HPC compute node and the HPC libraries pattern. So once I install those, not only will it install the patterns, but it will install all of the packages that are associated with those patterns. So I'll press Y, and it just so happens that as I've been going through practicing this demo, I should have removed all of the other packages as well, and I didn't. I'm sorry. And I'm only recognizing that particularly here now. I've been through this a couple of times and missed that particular detail. That's okay. If you were to be running this, this would install all of the packages as well as the patterns, all the packages that are associated with the patterns. Having done that, then I've got exactly what I need to have my my compute node acting as an HPC compute node with all of the right software installed associated with this pattern. I need to do that also for my head node. And for the head node, I'm going to end up installing the HPC workload server. I could turn the head node also into a compute node, and so install all three of these patterns if I wanted to, just depending on what my cluster is intended to do and what the kind of resources that I have. Nevertheless, with that particular detail completed, I've got the software I need to be able to begin to configure the rest of this cluster from the head node in order to make it functional. I really don't need to do anything specific now to any of the compute nodes. Basically, everything that's left to be done will be done from the head node. So here we are on the head node, and the next step that we want to undertake is to get NFS working correctly. Now, you don't have to have NFS in an HPC environment, but NFS is a common way of sharing disk, particularly for users' home directories. And there are a variety of other uses for NFS as well, but with the variety of users that you're going to have making use of your cluster, you would typically have a shared disk using NFS. And just as a side note, it would be interesting, a good use case for SUSE Enterprise Storage instead of NFS in this particular circumstance. So let me recommend that you investigate that as well. But just for the purposes of this environment, for this demonstration, we're going to use NFS. As a small detail here, you'll note that I now have a little extra space here on the margin on the left, and I've cut out the full screen details that I'm sharing here as I'm capturing this, just so it's less of a distraction and you can see better. You can now see the stuff that's on the left column. So for NFS, there are ways that you could do this by hand, but YAST is a particularly helpful way to do this. YAST walks you through the whole process of doing this, so we'll just quickly do it that way. First, note that I'm using this head node as my exported file system that all of the other compute nodes will mount. That's not an ideal circumstance. You wouldn't want to do that in a production high-performance computing environment, but here for this demo, it doesn't matter. So on the head node, I have a disk here, a XVDN disk, a block device that is going to be used for my NFS exporting. And so there are several ways that you can use this. We could use parthead, or we'll just use fdisk dev xvdn, and we'll create a new partition number 1. We'll use all of the disk, and it still has stuff from when I previously ran this demo when I was practicing it. So it's got remnant information there that I'm just going to overwrite. And so the signature will now be, the XFS signature will be removed, so I'll press W to write my partition information. And so now I have a partition that I can use. So we'll run fdisk-list again and see this time that I now have a partition on the disk, and those are its partition characteristics, a 30 gig disk that I can use now for NFS. Can't use it as a NFS file system without a file system yet, so we'll put XFS on it. We'll make FS XFS dev xvdn vdn1, and that'll be really quick just because it's a generally small disk. Having now a file system, I can use YAST to configure the NFS server, which I will do here. And again, this has got some artifacts from my having done this earlier. Normally, this would come up by default as a do not start, and it wouldn't have the NFS v4 information down there. But for this demo, that's not such a big deal. Sorry that that's that way. I'm going to start it up by default. If I had a firewall, I'd want to make sure that I have openings in the firewall for it to go through. And of course, in this demonstration environment, you remember I mentioned that I had to open up holes in the security group for ports to be open in AWS in order to share NFS, which is the equivalent of this firewall setting here. And then I intend to use NFS v4, so I've enabled v4, and I've given it the domain name that matches the domain information that I've been using consistently through this demo. So, and I'm not going to use security, the GSS security, on this particular demo. With that information now set, I'll press Alt-N. And now I need to create some exports, and that's easy to do. Let's go ahead and press Alt-D, and that will now create a directory that we want to export. And the directory that we want to export is going to be exports NFS home. We'll make sure that our homes are stored there. I'll press Alt-O for OK. Doesn't exist. Well, see, now I have a problem. I made a mistake here of not mounting that particular file system yet. And if I create it here, then that's not going to be what I want to have happen. So that's not too big a deal here. It's going to ruin the screen slightly, but not such a problem. I'll press Control-Z. And whoops, did I not move my cursor? I didn't. So press Control Z. And am I still recording? Looks like I'm still recording. So what we need to do now is make dir, what did I say? Exports NFS home. Yeah, that sounds right. I don't have anything there yet, so we'll have to do -P. And with that now created, we should be okay. I'll put that back in the foreground, and we can say yes here. Ah, good. Now we need to change some of the options here. The host wildcard is just fine. We don't care in this contrived environment that's going to be highly protected in its little security group in AWS. I'm okay to just allow all the hosts to have access. I want all of the hosts within the security group to have access, so we'll use the asterisk wildcard there. But I do need to change the options, because here at the beginning of the options, it's going to mount it as read-only, and this is going to be the home directories for the users, so we want to make sure that the users have read-write access to their home directories. So I'll then press Alt-O for OK again. I'll look at the summary of the information here and see that I do have the right directory here, and I have the right options here. Everything looks good. I'll press Alt-F to finish the configuration of my NFS server. Very good. So now I still have, I think, a problem, because I didn't ever mount that file system, did I? That was another thing I should have done here previously. That's easy to fix. You'll see now I have exports NFS home, and that exists, but I haven't ever mounted the file system here. It's not a big deal. Fix that here by vi etc. Oh, I've got an artifact there. That's okay. etc FS tab, and we'll need to then add here dev xvdn1. That's correct. And we'll mount that on exports. Yeah, that's exactly what I want. We'll have XFS file system, the defaults, and then have it behave as such. Good. So we'll right quit that, and then we'll look that we have an exports directory. We have what we created there, which was a mistake, right? rmdir, etc NFS home, not etc, exports NFS home. And now we should be able to mount that. We'll mount etc, what did I call that? Exports, yeah, exports, just like that. So now when we look at exports, it's there. And we look at mount, it's clearly mounted right there with the read-write option that we wanted. Okay, so now we have to make that directory again, and it will be much happier. NFS home. And just looking at exports, there's the directory. So with that done, then we need to make sure that we export it, which it should have done. Cat etc exports, and indeed it should now be NFS exported and ready for us to mount it on the remote nodes. That finishes then our portion of this demo where we're creating the NFS server, and the next thing we'll want to do is then create the NFS client configuration so that the compute nodes will be able to take advantage of this. A very common approach to an HPC environment is to have a shared disk amongst all of the different compute nodes, and the normal way of doing this, a very common way of doing that, is using NFS. So we need to configure NFS in our environment to be able to have a shared disk. In an enterprise environment, you would likely have a more sophisticated setup than this in our demo environment. You'd have a dedicated NFS server and probably multiple NFS servers for redundancy. But in this simple example, we've just got this simple way of demonstrating it by having a specific partition, a block device that is available here on the head node. You can see that here on the display. I've got this XVDN1 partition that I have created to be this NFS export. And we're going to go ahead and create a directory structure here on the head node that will mount this specific file system. Okay, so in this case, we're going to mount that onto a directory structure that we have created called local home. And I've created that here already. We've got local home here as the mount point for this NFS mount. And it's not NFS here. On this machine, it's going to be local. That's why we call it local home. And you may have a different naming structure for this, and that's perfectly fine. So we'll go ahead and now create that file system on that disk. And let's see. Yeah, I've already got a partition there, so I just probably need to make the file system there, and that's exactly what we need to do. So we'll make it an XFS file system. Make FS XFS and dev XVDN1. Good. Okay, that's all we needed. So now we just need to mount that on the local home. Yeah, we'll do that. Mount dev XVDN1 on local home. Good, that's exactly what we want. And then I've probably already got that in my FS tab. Let's go ahead and check my Etsy FS tab. And yeah, indeed, I do. So here on XVDN1, we'll want to mount that on localhost as an XFS. And with all the default mount options and zeros here, because we don't want to have to do file system checking and all that kind of stuff. So we're good to have that then mounted correctly. You'll notice now that we want to create an NFS home directory here underneath that local home, which is where we're going to end up mounting this. This is still a holdover from, again, my having done this demo for myself n number of times before doing this recording. Should have had the forethought to remove this beforehand, but that's okay, because we're just going to rewrite it here in a moment anyway. So then make directory localhost NFS home. And then we just need to export it. Now, of course, if you are familiar with NFS, you can do all this by hand. You'll know how to run all of the commands that are necessary to do this. But just for convenience sake and for the sake of demonstrating how to do this with YAST, we'll go ahead and use YAST to do this. So NFS server is our module that we'll run. We'll run the YAST configuration of the NFS server. And I've still got defaults in here from when I was doing this before. This would normally be set to do not start, so we'd need to change this to start. If you have a firewall installed, you'd want to disable the ports for the firewall, open up the ports for the get through the firewall. In our particular case, don't have a firewall installed. We'll go ahead and enable NFS v4. You don't necessarily have to if you don't want to use v4, but in that case I am. And for v4 I have to give it a domain name, which I'm going to call it the same as everything else I have been calling in this particular cluster. So having set that, everything looks fine there. And I could certainly use GSS security if I was concerned about the security. In this particular case, I don't want to. So I'll press Alt-N to continue to the next screen. Good. So I have this cleared out, and this is be easy to recreate now. So I need to export a directory, and the directory that I'm going to export is, I'm going to use Alt-D to add a directory, and the directory I want to export is localhost NFS home. I could browse for it if I wanted to, but that's the name of the directory that I just created, so I don't need to browse for it. I'll press Alt O for OK. And then the host wildcard, I want to let anybody within my cluster go ahead and access it, and I'm sufficiently contained that I don't need to worry about securing this any more than just the host wildcard. That'll be fine. And then I'll change to options by pressing Alt-P, and I need to go to the beginning of this because I need to change the read-only to read-write. This is going to be the home directories for the users in my cluster, so I want to be sure that they have read-write access to their home directories. So having changed that to read-write, I'll press Alt-O for OK, and it's written out the options all correctly down here in the second part of here, and I'm good. All I have to do is press Alt-Finish. And I should have NFS going. Let's go ahead and say export FS, and it is showing me that I am exporting that file system for those users. As far as the NFS server is concerned, that's it. We're finished. We have everything that we need to set up so that users can have this set up so that users can have this as their home directory. All right, we left off by creating the NFS server, and now we just need to create the NFS client configuration. And I'll just to demonstrate this on one of the client nodes, one of the compute nodes, and leave the rest up to your imagination for other ways that for the other nodes in the cluster that you would be doing. And of course, there are ways to automate this. You could be using Werewolf if you wanted to, or a variety of other automated mechanisms, like with Salt or with SUSE Manager. There are a variety of different ways that you could do this. But because this is a simple demo and I just want to show the fundamental aspects of it, this is how we'll accomplish this by shelling into AIML HPC Compute 1. And here on Compute 1, we've got our SUSE Linux Enterprise Server 15 SP1 running. And we'll just run YAST. So YAST, the NFS client module here for YAST. And it will then show us that there is nothing yet to mount. We haven't had any configurations here. We'll go ahead and press Alt-A to add something that we want to mount here. NFS server host then will be AIML HPC. Did I spell that right? Yeah. Head. And then I'll click the remote directory, and it's going to be exports, and the NFS home directory is what we're going to be mounting. And we don't need to worry about the mount options. We could just go ahead and take the defaults there, but we do need to tell it where to mount it, and we'll put it on NFS home. So with all those things set, of course, some of this could be very easily automated with the auto mounter from NIS, which was something that we'll end up doing in a moment. But this is the demonstration of just how to do the client aspects of this. So I'll press Alt-O for OK. That looks all correct. And we'll then, just for fun, let's look at the NFS settings. Yes, and because we may be using NFS v4, let's change that to our domain. So I'll press Alt-F here and change local domain to AIML HPC. And that looks correct to me. I'll press Alt-O for OK, and that should save it for us. And having done that, let's see if we have anything mounted. And there we do. Down at the bottom from AIML HPC head, we've got that exported directory mounted on NFS home. Just exactly what we want. And similarly, let's just cat etcfs tab and see that it has now added that exact data that we wanted here into our file system table. So we can look at NFS home. We don't have anything in there yet, but we will be adding users, and so users' home directories will show up there. Now it's really that simple. Of course, when you add 1,000 nodes, that ends up being much more complicated. You would want to do this in a more automated way with some of the tools, methods that I mentioned earlier, or your favorite, the most appropriate for you. You will, in this particular demo, know that I'm going to stop at this particular point and do this manually, the same way that I have for Compute Node 1 onto Compute Node 2, Compute Node 3, and Compute Node 4. But I'm not going to show you that here. It'd just be a waste of this recording time. Know that by the time we get to this next step, that those steps will be completed, and NFS client and NFS server will be working properly. In this step, we'll go ahead and configure the yellow pages, the NIS, the Network Information Service Process server, here on the head node. And you may have some other directory mechanism that exists in your organization that you may prefer to use. A common local centralized user management system that is used for HPC is NIS. So we'll just use that here, a quick demonstration of how to configure that and to do that easily here with YAST. I'm again here on the head node, logged in as root. I'll run YAST NIS _ server, and then press the enter key. And of course, you'll see here I've been doing this demonstration a few times as I've been practicing. The software is already installed. If it wasn't installed, it would say it's not installed. But of course, using this YAST module will cause the software to be installed. So no worries there. The configuration here asks whether I want to use this node as the NIS slave or as the master, or to do nothing and not set it up. I want to change this to be the master server. If you were in a real production environment, you would probably have a master and one or more slaves. But for this demo, we're just going to have the one master. And then I'll press Alt-N to go to the next screen. And again, an artifact of my having done this before is that it already has here the domain name, that whatever your domain name is intended to be. I'm using the same domain information for the NFS as I do for the NIS, which is the same concept that I'm using for all of the components of this particular demo. This is the Artificial Intelligence Machine Learning HPC demo, so I've called it AI ML HPC. So I've now typed that in there and use this host as also an NIS client. Make sure I've clicked that option to be have the head node also be a client. If I had slaves, if I had other servers in my cluster that would be slaves, I would go ahead and configure them here, but I don't, so I'll leave that unchecked. I don't need fast map distribution because I don't have any slaves, and that doesn't make any sense to do that. We'll go ahead and allow the users to change their passwords, so I'll press Alt-P, and just for variety's sake, we can go ahead and let them change their geckos field information, or the login shell. I'll leave the login shell unchecked, but leave the geckos field checked. And then once again, I would need to make sure that I have a hole in the firewall for this service. I don't have a firewall running in this particular case, but I have had to enable the appropriate ports in the AWS security group to allow this to work in my security group. Now I could change some other global settings. Well, we'll just look at that. I'll press Alt-O for the other global settings. These are all normal settings. If I had other password information, I could use the merge passwords. I don't need to do that, so I'll press Alt-O for OK. And then everything looks good here. I can press Alt-N to go to the next screen. And again, this is an artifact of my having done this before. I should have cleared this out, and I'm sorry I didn't. But we'll just want to make sure that we have these maps: AutoMaster, Group, Hosts, Password, and Shadow. In your organization, you may have others and additional ones here, but for this demo, those are the ones that I have selected. I'll go to the next screen then by pressing Alt-N. And again, this is an artifact from having done this previously. What you would see here, if you were doing this new, is just this top line that says the net mask of 255.0.0.0 for the 127 network. One thing that you need to do to have this work appropriately for your network is to create the net mask and network definition here that would fit your environment. Now I could be more selective here and have it just be the 10.0.10.0 network with a mask of the CIDR notation would be /24, but just for convenience sake here, and because I know I'm in an isolated environment, I'm just going to open it up to all networks here with that setting there, the second line. Having done that, I'm pretty much finished, and I can press Alt F to finish. We'll have it start the daemons. And there we go. So let's see now what we do happens when we type YP which. I indeed have YP running, and I'm content to have my YP mechanism running as a server here on the head node. Of course, YP running as just a server is only a part of the equation. I will next need to do the YP client, the NIS client, on the compute nodes. We'll do that next. We need to have the NIS client running in concert with the NIS server. Here on the head node, when we configured the NIS server, it automatically, or one of the options that we provided in the YAST module was to likewise set up the NIS client on this same node. So we've already got NIS working here. You can see YP, whoops, I meant YP which. That's what I'm trying to type here. And we've got that working fine, and we can do YP cat-k password. Let's see, what did I do wrong here? Oh, it's not the whole word, that's why, password. There we go. So we've got YP working just fine here on the head. The thing that we have to configure is the YP client on the compute nodes. So let's go ahead then and shell to one of the compute nodes, AIML-HPC-C1. And here we are on the compute node. As with all of these, there are several ways that you can configure this, but gratefully we've got the help of YAST when we are using SUSE, so we can just go ahead and run the NIS module for YAST. And again, I'm sorry, there's the artifact of my having done this before, but it's very simple. You just go through these settings here. I can go ahead and press Alt-U to use the NIS client. The default policy should be fine. For you, you've probably got a blank NIS domain value here. You just need to put in here the domain name that you set up when you created the server, and then the associated address of the NIS server. And in your case, you likely will have a more sophisticated enterprise deployment of this sort of environment. So you might have a master and one or more slaves to go with it. You'd need to make sure that you've got the slaves accounted for here too. You don't have to do this. It depends on how you're setting things up here, but you could certainly turn on broadcast, and that then makes it easier under certain circumstances to make sure that you're connecting to the domain in the proper way. Let's see. And if you have multiple domains, then that's the biggest reason to turn on broadcast here. In our case, we don't have that. You'd have to open up the firewall. Now, you probably know this if you are coming from a system administration side and have ever used NIS before, but NIS does not play well with current IP tables kinds of firewalls and host-based configuration, port-based configurations of firewalls. But if you're using just SUSE and SLES, this will work out pretty easily. So you just have to change this configuration here if you have the firewall running on both the client and on the server, and it should handle all of that. NIS bounces around a bunch of randomly generated ports, and so managing that is not the easiest thing to do. One other thing that we want to make sure that we do is integrate NIS with NFS. And so we'll go ahead and click, I'll press here the button Alt-S, which will send us to the NFS configuration here. And it should have inherited all this from what we already set up as the NFS client. This is really just running that NFS client YAST module and picking up all the information that it got from that module already. So that all looks good. We'll press Alt-OK. And then you'll want to we'll want to select the auto mounter, and I can use Alt-M to do that, to turn that on. And so that should be all we have to do to get an NIS running. I'll just press Alt-F to finish here, and we'll go ahead and let that finish, and it should be good. We'll type YP which, and yep, we've got YP running just fine on this machine. So I'll have to do the same thing on all of the other compute nodes, and make sure that the users that I set up will then all be a part of the NIS user database, which then will get shared through all of the clients in the NIS domain, and have a common user management all throughout all of the hosts on my cluster. On our HPC cluster, we need to have users. I need to create at least one user, and you probably would have a whole bunch of users. And this one user that we'll have here in the demo is going to be our data scientist. And she's going to need to have this account so that she can log in and run all of the tools that she needs to, that we're going to help her to facilitate for her with Jupyter later on in the demo. So to create a user in our HPC environment, there are lots of ways you can do it. This is Linux, but this is also SUSE Linux Enterprise Server, so we could certainly use YAST. Why not use a tool that's going to be very helpful to us? So we'll go ahead and run YAST and the users module for YAST, and that'll take a moment here to load. But this encapsulates all of the different capabilities of being able to create users and have all of the settings that you want for those users. And of course, we've got this integrated with NIS, which is going to be particularly helpful if you have a large cluster of systems where the unprivileged users will want to have access to those resources. In this example, we've already got a user created, and that's a necessary user for the AWS environment that we're in. So we don't want to mess with that. Before I create the user, let me show you a few other things here, such as this authentication settings tab over here. We'll press Alt-E to get to that so that you can see that NIS is going to be our authentication scheme for our users. That's going to be really helpful. Then I'm going to go to this Defaults for New Users tab. And here in our Defaults for New Users, we could change a whole bunch of these things, but for the purposes of this demo, we want to change this path prefix for home directory and use the NFS home directory. So I'll press Alt-P to get to that field. And remember, we set up NFS to share this big block device over NFS to all of the users as their home directory. This will be the prefix for that. Then we could go to groups, but we'll leave all those the defaults. We'll go back to the users tab here, and now we'll go ahead and create a user. And let's see, how did that save? I'm going to go back to Alt-F just to make sure that said, yeah, I didn't have to press anything to save those settings. Just want to make sure I didn't mess that up. Back to users, and I'll add a user, Alt-A. And however it is that you do your users, in this case, I'm just going to create a user called Data Scientist, and we'll have the username here be Scientist, and I'll give a password like that. And of course, if this was a real circumstance, you'd make it some password that's going to be changed by that user anyway, so that's less important of an activity here. I don't want this user to receive the system mail, and I don't want to disable user login. I want those to be the same. Now there is one other thing I want to change here, just because it'll facilitate my particular demo and certain things that I already have set a certain way. Let me just quickly change then to the Details tab. And yeah, I know it's not a sophisticated password. That's okay. We're just in a demo environment. You'll see here that the home directory has been populated by exactly what we expected it to be. Now it's going to be the NFS home that will be shared throughout all of the compute nodes in the cluster. What I want to change here, though, is this ID, and this is just a simple, silly thing because of my demo environment. I'm going to change that ID to 2 instead of 1. I could change all sorts of other things in here, but I won't, including other tabs such as the password settings, the public keys. We will deal with public keys here in just a second. So that will be important, but I'm going to do that differently than here in the YAST module. All right, I'll press Alt-O or OK, and that'll create the user in our environment. It's not writable. Now, what have I done here? Choose another path for the home directory. Let me pause for a moment and fix this. I apologize for that. Yeah, there's something that I had still messed up on the in the background from a previous part of the demo, and I'm sorry about that. But I'll press OK here and now try this again. I have now fixed that circumstance. It should be good now. And you'll see now I have listed in my list of users the scientist user, and should be good to go. Let me go ahead and press Alt-O for OK. That'll create the user and return me back to my bash shell here. And let's look that we have NFS home, and there's a scientist directory, and there's scientist ownership that's associated with that. And we'll grep scientist from the Etsy password file, and indeed that person is listed in our password file. So scientists should be able to log in now. Let's go ahead and prove that. Let's see. Well, what I could do is just do a sudo for right now, su scientist, and indeed here I have to go to my home directory. I'm happy as a lark here. I can see all of my skeleton from my home directory, and touch a file and see that I now have full rights here into my home directory. Even more important now is that I should be able to log into my the remote machines, the compute nodes on the cluster. Oh, yeah, I do want to see that I can do that, but I obviously can't do that until I have some better way of using SSH. I could do it here without the SSH keys if I wanted to do that. Let's try that. SSH AIM HPC client 1, and we'll do that. Yeah, see, I need keys to be able to do that. That's just a consequence of my running in the AWS environment, but that's no problem here. Let's go ahead and do that. SSH keygen, and we'll just use the default here. And I'm not going to have a password for this, which isn't necessarily a smart thing to do. But when we end up running MPI later, we want to make sure that we don't have keys associated with it anyway. So let's go ahead and just have a passwordless, a passphraseless key here. And that now should create a .ssh directory and .ssh. And so I've got my key. All I need to do here now is to echo id underscore rsa dot pub. Not echo, I need to cat. What am I thinking? Cat. ID, that's what happens when you record, is that you become rather stupid. Just because you're thinking more about typing things and speaking and not about what you're actually doing. Authorized keys. So we'll go ahead and do that. So now we should have an authorized key file, and let's chmod the 600 authorized keys. Did I spell authorized keys right? Yes, I did. Sometimes I leave a character out, and that causes all sorts of problems. So we'll look at the content there, and we've got the key. So now I should be able to SSH to that host with my key without the password. There you go. I'm perfectly content to now have access to all of the different hosts in the network via NIS, via NFS, and with my SSH authorization keys here in my HPC cluster, finishing that portion of this setup to create this unprivileged user named Scientist, who will now be able to connect to this cluster and perform all of the whatever it is that she is going to do in the context of her data science with HPC. And that's all we have to do here for this particular portion of the demo. We set out to do the things that I've listed here on the screen. I've showed you the general AWS environment. We installed the HPC module for SLES on the nodes in my HPC cluster. I set up the basic working environment for NIS and NFS, and we created a scientist user that's going to be the unprivileged user who's going to use our cluster for the data science. That then concludes this particular portion of the demo. We'll now move on to the next portion. In this portion of our demo, we need to get mpitch working. Now, we certainly could use any variety of MPI. There are a variety of MPI implementations that are supported and available in the SUSE HPC offering. I'm choosing to use mpitch mostly because I'm most familiar with it. I'm kind of an old school guy, and mpitch has been around for quite a long time. But there are other options, the more recent, more newer, more open variety, even though mpitch is obviously an open source offering. But you've got OpenMPI, you've got MVA pitch, which is a full MPI 2 and MPI version 3 implementation. You've got other workload management mechanisms like Slurm. And I really would like to be able to show you, if there were more time, how to use Slurm in this kind of an environment. But we're just trying to be focused, and obviously there's way more about HPC and way more about Jupyter and other data science approaches that we could show you, but trying to be very focused. In this particular demo, I'm going to just give the compute nodes some very simple workloads that I can leverage those compute nodes for the calculations of this workload, and I'm going to do that by way of the message passing interface of mpitch. So let's begin then this part of the demo. So I need to set up the head node and the compute nodes to have the mpitch software installed. By default, the mpitch software is not installed on any of the nodes. It's something that you need to install to get that particular version, that particular implementation of MPI as the choice that you want to have running on your system. If you recall, in a previous part of the demo, we installed certain patterns. And let me just show you this again. Although we didn't actually demonstrate it during the demo, I did make specific mention of the fact that you need to, on the head node, install that head node pattern, the workload server pattern, which I did. I didn't show you how to do it, but you extrapolate, you inferred from the information that I gave you that you needed to install this particular pattern. But that's really a very insignificant thing to do in the grand scheme of things. You'll see here that this particular pattern doesn't really do much for you. That particular pattern only installs these 3 different packages. One's that's not even really a package, but also slurm and slurm dbd. So that's good, that's important. Slurm is obviously an important central aspect of running an HPC cluster, but we don't have mpitch installed. Now, as a matter of fact, because of the image that I have installed, I do have some mpitch-like things that are installed, but not mpitch itself. You can see these things that have been installed. But that's what system administration is all about. That's what managing an HPC environment is all about. We need to install the packages that we want to use. So we'll do that by running zipper. Well, let's first search for what it is that we want to install. There are a few options here. And it's going to be a big long list that will scroll off the screen. There will be far more than what it is that we really need. I'll scroll up here, and the things that are particularly interesting for us here are the mpitch, obviously the mpitch package, but also we're going to install this MPI tests-mpitch package as well. So mpitch and MPI tests-mpitch. We'll just use zipper. I happen to have that in my buffer here, and that'll be easy to install by just doing that, and then mpitch itself, except I have to be able to type it correctly. That looks right. We'll install these and press Y to confirm. Excellent. I've got mpitch installed now on my head node. Now, one thing that also needs to happen here by way of configuring, installing and configuring mpitch is that I need to select it. Remember, you've got several different MPI choices. You have a tool called MPI Selector. I need to spell correctly. Stop talking and type. MPI Selector, and you actually have a menu version of this as well if you want this little text-based menuing system for selecting. But we'll go ahead and do mpitch selector and look at the options that we have. And I want to list, again, I could just use the menu-based system to do this, but you'll see I only have mpitch installed on this particular box. So I want to then set mpitch as my mpitch option now. So now that I've done that, that's going to set certain environment variables for any new shell session or any new interaction with this HPC environment, so that it will be using the MPI exec and the MPI CC and whatever the other MPI, MPI run, all those kinds of things for the MPI tasks that are going to be happening in this particular HPC cluster. Now I need to do these same things on the compute nodes. So I'll just demonstrate doing that for one of the compute nodes, and you can extrapolate from that example how you would do it on the other compute nodes. Now I could just SSH AIML HPC C1 and interactively do all of that installation, or I could just be a little bit more programmatic about it and just run a command from here and install -y. I have to pass it this -y so that it's non-interactive, but then just mpitch like that. And that should install mpitch and whatever dependencies that it has without my having to do any interactivity with it. Of course, if you are in a complex shop, this gets to be very tedious to have to do this. If you've got a lot of hosts, 1,000 compute nodes, you might not want to do it this way. That's when other tools may be appropriate for you, like Werewolf or SUSE Manager or even SALT, some other system configuration kind of tool. But we're just doing it the simplistic way here for this demo. So we'll go ahead and run that command here. That'll download mpitch and install it. Everything's cool. All right. I will leave to your exercise the installing of the mpitch package on the other nodes in the cluster. This is just the example way of doing it. With that, we should have, oh, wait. Of course, before I do anything else, I also have to do the same thing about the MPI selector, right? Yeah, I'm glad I stopped myself before I ended the recording. So we'll run MPI selector and the exact same thing, set mpitch. Did I type all of that correctly? Let me double check my typing. Yes, okay. So I press Enter key, and now that particular MPI implementation is the one that is selected on the compute node. Do that also for all of the other compute nodes in the cluster. For this portion of the demo, we want to start using MPI. We want to make sure that MPI is working. We have previously installed and configured mpitch for this particular cluster, and now we want to make sure that it's actually useful and functional. So in this part of the demo, I am no longer the root user in the cluster. I'm connected still to the head node in the cluster, but I'm connected to it as the scientist user. And as the scientist user, I want to perform some various tasks with MPI. To do that, lots of ways that we could do that, but one of the convenient ways to do it, and one of the tools that I like to use, it's really convenient and it's pretty nifty, I think, just comes from sample code from the mpitch developers. It's a tool that allows you to do various functions related to pi. And yes, pi is a very frequent tool, a very frequent whipping boy for all sorts of data science. In this particular example, in these pi calculations, you have to download the source code from the mpitch folks. It's not something that is packaged up and is readily available in SUSE Linux Enterprise Server. So to save time and to just ensure that access to the internet wasn't a problem for this part of the demo, I've pre-downloaded it, but I'll show you exactly what I did to download it. I have here in my scientist home directory a subdirectory that I have created called mpitch test. So we're going to cd into that directory, and you'll see the file that I have downloaded. It's just the standard tarball of sources that created mpitch version 3.2.1, which happens to be the same version of mpitch that we have running here on our cluster. So rpm-q I mpitch. You'll see that we've got the version 3.2.1 installed. So my sources match the running version of mpitch. And for the sample tool that does calculations with pi, it really wouldn't matter anyway. I mean, it's just the source. We're going to compile it. The command that I ran to get this was, you can see there on the screen, I just did a wget on a path from the mpitch.org website, and that's the path to get to this particular set of sources. Now, before I continue any farther with this, let me also show you one important detail about the operational environment of mpitch. Remember, we ran the mpitch selector, and we did that as root. And that made sure that the MPI selection would be consistent, would be universal for all of the users in this particular cluster. I could rerun that MPI selector for my scientist user to choose a different implementation of MPI if I wanted to. There aren't any others that are installed on my system, but I could, if I had something available, or if I happened to install some other MPI here local to my user, I could use MPI selector to select that. But one of the consequences of running the MPI selector is that it sets some environment variables, and I just wanted to show you those environment variables. Let's, instead of using less, let's just grep -i MPI. So I'm going to show you all of the environment variables that have MPI in their string. And there aren't a lot, but they are important. Note that our load library, our LD library path, now includes the path to my mpitch installation. This is inconsequential because I happen to be in that subdirectory. It's telling me what what the present working directory is. But manpath and path also have been added to include the mpitch implementation that I have selected with the MPI selector. That'll ensure that when I'm running a CC command, an MPI CC command, or if I'm running anything else that's going to be dependent upon my selection of MPI, it's going to choose this mpitch stuff. So here we, that includes MPI, what am I doing? Yeah, that's right, MPI CC. All right, let's do that. Which MPI CC is going to take it from where it's found that in the path, and MPI exec and any of the other things that we're going to use is going to use it from that particular selection. Wow. When I'm talking, I can't type, just like you. All right, well demonstrated. Let's now make use of this and extract this with tar xzf mpitch tar. And that won't take terribly long. It's going to just extract the sources into this current temporary directory. At least it's not supposed to take very long. I'm just going to take a quick drink of water while I'm waiting because I didn't think it would take that long. To a certain extent, this is taking a little longer because it's on an NFS drive instead of a local drive, but that's okay. Here we've extracted it. We'll CD into the directory structure, and in here we have an examples directory, and let's just look at examples. And in here you have a CPIC file. Well, actually, let's change into that directory. And just for fun, we'll see this is a CPI file. Yeah, I was kind of hoping that it would have more details about what this particular program will do in the header. Just an example, some documentation. It's not there, but it's a very small file. You can see how small it is. Let's just compile it, and we'll use MPI CC to compile it, CPI-C, and the output we want is that CPI executable, and we can't find MPI.h in our path. That's frustrating. But I actually did that on purpose because it just helps you to understand one of the frustrations of and the common occurrences of getting all this stuff to work properly. And as a very specific and deliberate aside here, I'll mention this is one of the kinds of things that, although I say it's a common occurrence under normal circumstances, this is one of the things that we hope to try to reduce these kinds of headaches, if not eliminate them entirely, by setting up this phenomenal solution at SUSE that is headed up by Alessandro Festa to provide an environment and tools wherein you can do all of this stuff without these kinds of headaches and challenges. Now, I can't tell you that it's going to eliminate this sort of thing entirely, but the whole reason I set up this failure here is to use it as an example of what people have to go through with this and what we hope to accomplish to make your life easier with SUSE solutions. All right, this very simple solution to this is we don't have all of the packages installed. Let's go ahead and do a zipper search again, and we're going to search for mpitch, and we'll just to reduce the clutter on the screen. I'll also similarly reduce the output with a grep. And come on, give us what we want. What we need is this mpitch devel package installed. That's going to provide that mpi.h file. Easy enough to do, except I can't do it as the scientist user. So in this environment, I have to go talk to my system administrator. Oh, I need this thing installed. Sometimes we can solve this as an unprivileged user in our own development environment. I could download the package. I could set my include path to be something different. But we'll go ahead and just exit out of here temporarily. I'll change to here, zipper in mpitch devel. I think I already highlighted that. Yeah, I did. And have the system administrator with root privileges install the package and exit out from being the root user and go back to being the scientist user, cd back into my directory. And in this course, when you have to contact the system administrator, that could take hours or maybe days, and maybe some approvals to get new things installed. What a pain. Yeah, we want to fix that kind of thing. But now I should be able to run mpicc without any problem and get that compiled. Woohoo! I now have a CPI command. Now, you don't have to know a lot about what CPI does. All it is a bunch of C functions that have to do with the computation of the digits of pi. It's kind of a cool thing. Whoops, I have to run it in the current directory. And this, without running any other arguments, it's just going to tell me what an approximation of pi is to a certain level of precision, and with from a cool data science perspective, some calculated possibility of the error rate in that calculation. What's also cool is that it's just going to run it as a single process, as a single thread, right here locally, and going to tell me how much time it takes. So from a data scientist perspective, from an MPI perspective, this is going to be really cool when I start using this as we start using MPI with this, which is exactly what I want to do now. From here, I'm going to use MPI exec. I'm going to tell it to use, I've got 4 compute nodes in my cluster, and I want to simplify the output. So I'm only just going to use a number of nodes, a number of processors of 4. But I need to tell it which hosts it is that I plan to use. And to do that, I just provide a comma delimited list. Now, there are other ways of doing this. I could use a -f and refer to some a text file that has a list of the hosts, like this syntax. But I can also just use this syntax of host and provide this comma delimited list. AIML HPC C1, AIM HPC C2. No, I left off an L. There we go. AIML HPC C3 and AIML HPC, C4 or -C4. And then I want to run the command CPI. All right, just so that I don't look foolish, I need you to know that this is not going to work. I'm going to press the enter key and it's going to just appear to be hung. And yeah, well, that's another reason why. That isn't exactly what I was expecting to have happen, but the hanging part here now is obviously happening. Now, the reason that it is hanging is because I'm in this AWS environment where MPI is using a random generated set of ports that I don't have open, and I have no way of predicting what it's going to do. So I have to pass here an environment variable to tell it to use a specific set of ports that I do have open in my firewall, my AWS security group. So let me just cancel that, and let me find that command, the environment variable that I have. Okay, I've extracted that from my notes here of which ports I have here, and now I'm going to recreate that command. You will probably not have to worry about this kind of thing in your HPC environment, but here in my AWS demo, I have to provide this environment variable. And the ports that I have opened are those that you can see listed. And just it's 100 ports. I don't even need that many, but I just picked a nice round number of ports. And there are several synonyms for this environment variable, but this is the easiest and most straightforward meaning that of the varieties that exist. So I just passed that to here, and this should work just fine. Oh, and just so you know, these were stale NFS handles that I have fixed, and so this shouldn't happen this time. All right, I'm going to run this again. Here we go. Press enter. And what happened here? 1 second while I investigate. Well, yeah, of course. Of course that's not going to work. Yeah, I'm sorry, I didn't even really need to pause there, because the moment I paused the recording, it was easy for me to recognize. When I pass this information, this command to MPI, which will then hand it off to the compute nodes, they need to know where CPI is. And of course it says, I have no idea what you're talking about with this CPI thing, because it's not in my path. And that was just short-sighted of me. I'm going to recall the previous command here, and I just need to tell it where to find it. So from my home directory, which is going to be the same home directory for the scientist user across all of these compute nodes, because I'm using NIS and NFS. So it's in my NFS home directory, and it's going to be in this mpitch source directory that I have going on here, and in the examples directory. So with the qualified path here now, it should be able to find it and be able to exec that command. All right, I'm going to run it again. Yep, I was right. Finally worked. Now this is really, really cool. This CPI tool, which is intended for this kind of example to demonstrate these kinds of capabilities, I handed off a portion of this calculation to process. Well, I'm doing this 4 times because I passed it this N4, and I passed off portion 0 of it to HPC C1, first compute node. Portion 2 went to C3. Portion 1 went to C2, etc., etc., etc. And now it has calculated pi. Let's see, I've still got it on the screen here. It's a slightly different value, and my error rate here is also slightly different. Can I tell if it's a higher calculation or a lower error calculation there? That's not worth figuring out. We're not data scientists, we don't care. But you can see that this now works by not just having AIM, the head node, doing this calculation. We passed off calculation responsibilities to the multiple HPC nodes, the compute nodes in our HPC cluster, to do the calculations for us. And you'll see also that when we ran it locally, it was really fast. Well, it's because calculating pi to this just very simple number of digits of precision locally, and then getting the details back, is obviously going to be really, really fast. Using just this default behavior of pi with these very few digits of precision is not terribly interesting. But even so, passing it off to 4 different compute nodes for 4 different threads, that's still pretty fast even in wall clock time. Let's do it a little bit differently then here, and let's change the n value to 64 this time. And I'll go ahead and execute that. And now it does take a little bit longer because you've got all the overhead of sending it out and collecting the data back and reassembling it. But in theory, the more that you hand off to process different processes on different processors across different nodes throughout your cluster, and with the greater the complexity of the calculation, the better the payoff in terms of lower errors and faster compute times. When we get later in the demo, we'll have a far more complicated calculation that you'll see the benefits that come from passing it off and getting the data back instead of just using the one head node for those calculations. So in summary here, we have installed the MPitch example here for my unprivileged scientist user and ran some examples of MPitch from this user. So in conclusion to this section, we've made sure that the message passing interface of MPitch is working. It's working for a unprivileged user, and this unprivileged user is able to run simple calculative commands and distributing that work to the compute nodes in the HPC cluster. Now, we haven't done any good data science yet, but at least to this point now we understand that we've got the ability to do all sorts of complex calculations using an HPC cluster, which we will later tie into some data science tools like Jupyter Hub. Next in our process of getting some data science joined together with HPC is we're going to take advantage of Jupyter Hub. Now, you have heard a little bit from Alessandro the great thing that Jupyter Hub is, and how Jupyter Notebooks, Jupyter Lab, and Jupyter Hub are all going to be part of our AI and ML offerings and solutions that are going to be provided by SUSE. We're going to take advantage of this in our demonstration here and put these things together so that we can have Jupyter and Jupyter Hub and Jupyter Notebooks take advantage of our high performance computing cluster and the compute nodes that are in there. So we've got this great tool that allows a broad collaboration for data scientists. And you can put together the means whereby you have the notation for the reproducibility of all sorts of calculations that go on in your data science, where you've got a live flow, a live stream of what's going on in terms of code that glues logic together. You've got equations, you've got visualizations, all of this put together in a textual format with as much or as little of the instructions, the inline instructions of what's going on with this particular science. That's one of the cool things about Jupyter Notebooks. And the Jupyter Hub allows you to put all these things together. You can have multiple notebooks used by multiple users, all within this single cloud of computing resources. And in our case, this cloud of computing resources is going to be a high performance computing cluster. So in this section of the demo, we're going to install and configure Jupyter Hub. The Jupyter Hub code, the Jupyter Hub software, is going to run on the HPC head node in our cluster. Jupyter Hub is based almost entirely on Python, but there are other pluggable modular aspects of it that could exploit capabilities from other languages as well. And one of the key features that is used within Jupyter Hub to make all this possible in a parallel environment, in a distributed environment, is IPython, and more specifically, a small piece of IPython that's known as IPy parallel. And that will allow us to distribute this work that is defined and described within a Jupyter notebook. So in this section of the demo, we will need to install Jupyter Hub here on the head node of our HPC cluster. So I am connected to the head node, and it's entirely possible to install and run Jupyter Hub with a non-privileged user. it's designed to do that. All of these Python tools routinely are able to be installed as a non-privileged user within the file system structure of the non-privileged user's home directory. But to be particularly useful in this environment, in our high-performance computing environment, it's best to simply install it as the root user. Now, bear in mind, there will be a variety of other aspects of this demonstration and of the operation of these tools that you will install parts as the unprivileged user, known as scientist in this example. But for the overall implementation of Jupyter Hub, for the overall installation of Jupyter Hub, we're going to do that as the root user here on the head node of the HPC cluster. Now, eventually, all of this will be part of a tool set that can be installed as RPMs from delivery from SUSE. That's not the case yet. For this demo here, I'm going to show you how this is done just from an everyday normal user's perspective and not from this cool solution that we will end up providing. As the root user here on head, I'm going to install this Python code in a way that Python wants to install it, and that is by using pip. This is the Python package manager. So with pip, we'll run install. This is going to install software from the internet. So if you've got concerns about security, and right that you should, you may not like this approach. That's one of the good reasons that SUSE provides value by packaging these kinds of things up, which will come later. But here we'll just use it from the standard Python repositories upstream, and we run Jupyter Hub. Now, Jupyter Hub by itself is not useful. It's got a whole bunch of dependencies. There's the Jupyter package itself, you've got the notebook package, and a bunch of other contributing packages, but you'll see those dependencies get installed when I install Jupyter Hub here. Well, and it's going to go really fast, and there you go. It's already done. There are a bunch of things that I already had installed and is inconsequential. There are these seeming to be errors that are involved here in terms of could not build wheels for these things since the package wheel is not installed, and that's easy to overcome here if we start then instead by installing wheels. Oh, that's interesting. Oh, it'd help if I actually just typed it right. Install wheel is what I meant to do. There we go. That's installed, and then we should be able to not have those errors anymore. I'll go back and rerun this, and all the requirements are already satisfied for all those things that it was complaining about with wheel. As I've mentioned previously, there are artifacts that are still installed from previous attempts to practice attempts of going through all this demonstration. So you just see some of the leftovers from that. Nevertheless, we now have Jupyter Hub and all of its dependencies installed. Now, if we wanted to be just particularly pedestrian about how Jupyter Hub should be run on our system here, we could just run it. Just type the word Jupyter Hub and execute it, and it would try to run. And it's going to fail. I actually knew this was going to happen because I wanted to point out that there's still an additional dependency that's going to be required here. But we could just run it here from the command line. But that's not a particularly good system administration approach. That's not a good enterprise approach. We want to have this run more as a service, a startable and stoppable kind of service. So we're going to get to that in a moment. I first need to fix this startup error. What it's trying to do here is, as an application, it needs to present itself as a web application. This is, after all, a sophisticated web application, and it needs to have another piece of this puzzle as a dependency installed. But this kind of functionality doesn't exist as a Python package or as Python code. This particular dependency is a Node code, Node.js as a matter of fact. So we need to use npm, the JavaScript package manager, to install this configurable HTTP proxy code. So that's easy enough to do, because what we end up wanting to have happen here is to have this application run fronted on port 8000. Now there's a whole bunch of other stuff that's going to be happening through other ports in the background, but the main user interface is going to be hosted there on port 8000. And so we need the configurable HTTP proxy. So to do that, we'll use npm, and let's see, I forget what I think it's just install, and we need to install it globally, and then the name of the package, which we'll just paste there. I think that's all we have to do. And it does look like, yeah, I think that's done exactly what we need it to do. So to now run this again from the command line and just have it run here from my desktop here on this bash shell session, we'll just come back here and run Jupyter Hub. And it's running. Here we have that it's starting and listening here on port 8000. That's wonderful. Let me go ahead and put this in the background. And of course, this is something that it's technically possible to do, but it's not the most appropriate thing to do. I'll just put it there in the background, and we can demonstrate that it is type BG there, and demonstrate that it is actually listening on port 8000. So here we go, ss-plen to list the ports that we have here, and grep for 8000. And there we do indeed have port 8000 being heard, and it is being fronted by Node.js, which is exactly what we told it to do. Now, an important detail is, of course, in my Amazon Web Services environment, I have to allow port 8000 to be available. And not only that, I have to make sure that port 8000 is available to the outside so that I can get to it here from my demonstration environment. So I've done all of that in AWS. You may, in my security group in AWS, you may have to do similar things to your firewall if you are in a protected environment. But once you get port 8000 exposed and allowed to be seen from the outside so that people can attach to it from their web browsers, everything else is going to be happening on the back end here on this head node, and you don't need to worry about opening any other ports. So that's the basics of simply having Jupyter Hub run. Now, we haven't used it yet. We're going to get to where we're using it, but that's going to be here in the next step of our process. The next thing that we need to do is realize that running Jupyter Hub just like this in the background of this particular bash session is just not a good enterprise approach here. So let's just bring this back to the foreground and kill it. I'll press Control C. We want it to die. And we can go ahead and show that it's not running anymore. Port 8000 is not being served anymore. No, nothing's listening on port 8000. And we don't have anything running that's called Jupyter. We want to turn this into a service. Again, eventually, you won't have to do this kind of thing. As part of the solutions that we are developing that are going to be particularly useful for a good enterprise consumer of this, we'll have RPMized all of this and created services, systemd services for it. But for this demo, I have to do that myself. I've already created a serviced unit file, and have here the just very sparse details of what would make up a useful service file, unit file. It's not the greatest, but I'm telling you, it's going to work. It'll work just fine for our purposes here. All I have to do then is copy that service file and put it into the place where systemd makes good use of it. User lib systemd system. Oop, I don't want to list everything that's there. And yeah, that syntax looks right to me. And then I need to use the system control tool to do a daemon reload, and to pick up the changes that I have made to this service file. And now that I've done that, I need to enable the new service that I have created. Enable user lib systemd system. Oh, what am I doing? I just need to call it by name because I use daemon reload. I don't have to use the fully qualified path for it. So Jupyter hub.service. And then let's start it up. Start. Well, it didn't tell us anything. That may be good. It might not necessarily be good. Let's see what status tells us. And it didn't work. Okay, now I knew this was going to happen. So all we have to do is now fix this up so that it will work for Jupyter. Notice that it's telling us that it is missing a file. Now that scrolled off the screen. Well, actually, let's just do that so you can see it. I'll redo the status, and now I can go to the right and say that it's missing a. Oh, wait a second. Changed-er. What is this complaining about? Failed at step changed-er spawning user bin. Oh, yeah. So it's not telling us exactly what's wrong, but I'll tell you what's wrong because if we look at that file, I'll look at the source of that, which is here, it's trying to find this working directory, Jupyter Hub, which doesn't exist. We don't have this RPMized, and I told it to look in this directory for this particular thing, and it's not there yet. So if we look at etc, there's just nothing there. I'm trying to tab complete it, and there's nothing there. So let's go ahead and make it Jupyter Hub. Doesn't exist. Come back to the beginning of the line and do a make-dir. And then it will cd into that directory. And here we want to put in our configuration file for Jupyter Hub. Every good system application should have a comprehensive configuration file, and Jupyter Hub is no different. So we want to run Jupyter. I forget what the syntax is for this. That's not it. Oh, that was it. I passed. Oh, no, here it is. This is the screen that we want. Sorry, I had to just recall that from my command history because I couldn't remember the syntax. But I'm just going to add this switch now to running Jupyter Hub. And because I'm not in that directory. Did I cd to that? Yes, I did. I'm inside that directory. I simply need to run this, and it will create a configuration file for me in my current working directory. So let's just look at that file and know that it's huge, right? We've got 977 lines of code representing configuration. Now, of course, a lot of it is comments and documentation, but it's very comprehensive in the kinds of things that you can configure, like log format and log level, all of these different things. You can tell it which port to listen on and all sorts of configurable details that are associated with a good enterprise application. We're going to leave all of the defaults because the defaults will be adequate for us for this demonstration. So I'll quit out of that file, and now we'll try to restart the application again. We'll do a restart of Jupyter Hub service. Now again, I don't get any output, so that could be good, but it might not necessarily be good either. Let's check the status of our service running now. Aha! Well, now that I created that working directory and created the configuration file that goes with it, I've got it working now. It says that it's in the state of being loaded and active, and I can see all of this helpful information that it is using, including that it is listening on port 8000 and a variety of other things that are happening that we don't necessarily care about to make it functional behind the scenes. So with that, I can again look to see that it is running. will grep for port 8000. And indeed, Node.js is listening on port 8000, and we have a functional Jupyter Hub running as a service, and one that will restart if I ever need to reboot the HPC head node here where it is running. Now that we've seen from the engine side, from the command line side, from the service side, that Jupyter Hub is running on our head node, I want to demonstrate that it is actually running from an end user perspective, from a client perspective. So here now I have the web browser running, and I just need to access the external IP address. In this case, this is going to be my AWS assigned external IP address. And we're going to connect to port 8000. We have the correct notation here for connecting to this where it is listening. I'll press the Enter key, and there we have it. We see that Jupyter Hub is running by name up here in the upper left-hand corner, and we have a sign in here. If we were to be running just a regular Jupyter instance for a Jupyter notebook, it would behave a little bit differently. And I'm not going to go into the details of that because that's not the focus of this particular demonstration. Running Jupyter Hub, however, now provides for you a multi-user collaboration environment where multiple people can sign in using their credentials from the HPC cluster to the Jupyter Hub. So that's what's going to end up being in the next section of the demonstration. Nevertheless, here we have evidence of Jupyter Hub running, and the access here now available via a web user interface. So in conclusion for this section, we've gone through the process of installing the Jupyter Hub and configuring, well, showing how Jupyter Hub can be configured with its configuration file, and turning it into an appropriate service, a systemd service, so that it can run as a good enterprise tool here on our HPC head node. So we've got the Jupyter Hub running on the HPC head node, and I've explained, although it wasn't blatantly obvious, certainly by installing it using pip, we've shown that it's largely based on Python. But similarly, we have installed a tool that is a Node.js, a JavaScript tool, to allow it to function appropriately as a web front end, listening on port 8000. Now, this last detail about IPython isn't blatantly obvious yet, and that's certainly going to be more evident as we get into the last section of using the tool. But we've set the stage now for Jupyter Hub to run this extensive Python tool that's going to allow us to collaborate with our Jupyter notebooks here in our cluster. So let's take advantage of this notebook capability and have some fun with it. Let's show how the notebook can be benefited by our high-performance computing environment. We can do all sorts of data science just with a standalone Jupyter notebook. As a standard user, we can do all sorts of things using a single node. The best thing about this demonstration and about the promise that comes with it is that now you can use a high-performance cluster and all of the compute capabilities that stand behind it to amplify the ability to do good data science. So in this last section, we're going to use the Jupyter Notebook at scale using the SUSE HPC that we have set up. So we're going to use our standard scientist user to run a Jupyter Notebook set of tasks, and we're going to compare and contrast that between using it in more of a standalone single system environment with using it in a distributed MPI environment with HPC. So as the data scientist wants to use the Jupyter Hub, all that data scientist needs to do is to start up this browser like you see here on the screen and go to the URL that we have here. You don't necessarily need that fully qualified. You just go to the 8000 port and it gets redirected like that to the login screen, and then to log in with the appropriate credentials. Now, there is no need to keep a separate database of users. There's no separate user access table for the Jupyter Hub. The Jupyter Hub users are simply going to use the exact same credentials that they have on the HPC system, the cluster. So the system administrator for the HPC cluster, who has provided this Jupyter Hub service, will create users in the high performance computing environment, provide that user with a password, and then whether that data scientist is using that username and password for direct access to the high performance computing system or to Jupyter Hub, it's exactly the same. So earlier on in this demonstration, I created a user called Scientist, and I gave that scientist user a password. You don't know what that is, but I have it here. But each data scientist would know what his or her credentials are. Simply type it in there and then click on Sign In. And then it will take you through, that was actually really quick. It should take a moment to instantiate some information here as it starts up the Jupyter Hub, and then presents the user his or her user environment of notebooks for the Jupyter Hub. Any data scientist who's ever used Jupyter and Jupyter Notebooks would understand what this is right here as this appears. Now this is a very blank and Spartan environment here because I don't have anything yet. I'm the data scientist and I've got a brand new environment. And the fun here of this demonstration is creating stuff that's going to be working here for this data scientist. Now I want to just give a little tour here of what we can see before we do anything particularly functional. Here in the Jupyter Hub, we've got all the framework here of any other Jupyter Notebook environment, but a few extra things here that make it part of the Jupyter Hub. So here we've just got a regular directory structure, a file system structure here, where you're going to be able to store files, and all of this is a reflection of what's available down at the file system level in the Linux home directory for this particular user. In this case, we're the scientist user. And so you've got some tabs here that help you with some other aspects that will be more useful later that I just want to show. First here you've got this running tab, and this will tell you which notebook terminals that you have running and which actual notebooks are running. Right now, because we don't have anything in this particular scientist user notebook environment yet, you would expect here, this is the first time that we're logging in, nothing is running. The next tab that you see here is this IPython clusters tab, and as we create profiles for interacting with the cluster, with the high performance computing cluster or other non-high performance computing cluster aspects for parallelizing workloads, you will see profiles show up here. So we will see something more interesting there later. All right, let me go back to the Files tab. And here in the Files tab is where you can create the actual notebook information. And there are a few ways that you can do this. There are a few features of creating new capabilities here in your notebooks. We'll start here by this new widget. We'll click on New, and it will pop up some capabilities. We can create a regular Python 3 notebook, or we can just create a new folder, or we can create a text file. And also we can start up a regular bash-like terminal to interact with the operating system on the backside. You also have on this upper right-hand collection of widgets, an upload link, a button, a widget, that if we were to click on that, we could upload all sorts of things that would be files that we have stored down in my file system. And if something, for whatever reason, is changed and you don't think it's being reflected here on the web UI, you can always click on this refresh notebook list and it would just refresh whatever's there on the screen. As you would expect with some sort of file system browser, you can also have these little headers and sort on them. You've got the name field here, and you have a last modified field here, and then a file size. Since these are directories, they don't have a file size, and you can sort by them. So if it's being sorted right now, you can see that little arrow that shows down. If I wanted to sort the opposite direction, backward, I click on it and now it shows up. I click on it again and it'll toggle those capabilities. You can see that it's got these check boxes here. If I wanted to move a directory or rename a directory, I could click on it and it gives these options here, including deleting it. Now I don't want to delete this stuff here. I don't want to delete anything. But if I click on any of these items, then I've got these new function tabs, function buttons that appear up here. Lastly, this top menu item here that's on the header, you've got two buttons up here. You've got a control panel that I can try to stop the Jupyter Hub server, and then I can only stop my own access to it. Or I can just switch back over to my server to show exactly what it was that I saw before. What this is really showing is the opportunity to have multiple environments. I could actually click on this control panel and switch to a different server, which is kind of a cool multi-level functionality capability. And then of course I could log out. If I wanted to log in as a different user, I would want to first log out from my account that's connected as, in this case, scientist in this Jupyter Hub. All right, that's just a quick overview, a little tour of the main Jupyter Hub screen here when you log in. Next, let's try uploading something interesting that we can use as a Jupyter notebook. You can get Jupyter notebooks from a lot of different places. You can download them from Kaggle. You can download them from GitHub. I actually have stored these simple tutorial ones from in my GitHub account, and I'll somehow share that information with you if that's interesting. But all we have to do is click on this upload button, and I hope you can see that. I think you can see that. And that should pop up then a dialog box, and I've got an MPI directory that we can click on here. And in there I have this directory called Jupyter Notebooks. And here I've got two. I have a local parallel demo and an MPI demo file here. Let's start with this one. And that then will give us an opportunity to change the name if we want to, or just leave it the way that we want to. But then click on this upload directory button. So clicking on that will now upload this file into our workspace. And then let's do the same thing with the other one. We'll end up using it later, but we'll click on that upload button again, double click on the MPI one, won't make any changes. Well, let's just for fun, MPI demo, and then click on the upload button. So now we have two different files that are notebooks that are going to be used in our demo and are going to contain all of the notebook data that is representative of everything that a data scientist recognizes as useful from a Jupyter notebook perspective. So let's click on the local parallel one here, and that will open up a new browser tab. You see we've got a whole brand new browser tab over here, and it loads it up as a regular Jupyter notebook. Now you might not know much about Jupyter notebooks. The system administrator, the DevOps guys really don't understand Jupyter Notebooks very well. And that's okay. You don't have to understand this to the level that a data scientist does. But trust me, the data scientists in the room, they know everything there is to know about this stuff. And this is cool, useful, helpful stuff. This is their lifeblood to be able to use great computational tools with this Jupyter Notebook mechanism. But you can see the instructions, you can see some of the output, you can even see some comments. This particular notebook is not as fully outfitted with more interesting stuff as the other example that I have, which is really well documented and is the one that we'll walk through more closely and carefully. But wanted to point out, just as far as this part of the demo is concerned, that I have launched this notebook and I have all of the notebook controls that a data scientist loves and appreciates. From this point on, we need to be logged back into the HPC cluster on the head node as the scientist user. And also, from this point on, for a little bit, this is really, really technically complicated. That is to say, it's technically complicated from a data scientist's perspective. This is the kind of area where data scientists know enough about the infrastructure and Linux to be dangerous, and that make the DevOps guys kind of nervous. But it's okay. It's just that it's tedious and it's technically sophisticated, and something that the data scientists aren't always particularly good at, and it's not easy. Here on this particular part of the exercise, we need to use IPython to create a profile that will be able to be integrated, to be launched from the notebook to allow for parallel computation from the notebook. So we'll go ahead and use IPython. How do you spell Python? IPython profile create. And we're creating a profile that we will need to customize that will allow this integration between the notebook and the HPC parallelization cluster capabilities. We're going to start with a simple profile that is one that is going to not use the HPC mechanism, but will allow for parallelization of distributed work just on the head node, so that you can use the multiprocessor capabilities on the head node, but not as a distributed workload through the compute nodes of the HPC cluster. So we need to use the -- parallel switch, and we will call the profile, we need to give the profile a name. Profile equals, well, we'll call it parallel, shall we? Whoops, parallel. A very simple profile for a parallel computational model capability on the head node. See where it is being stored. It is going to be located here in these several files underneath this .ipython directory structure. So let's change into that directory structure. .ipython. And then, well, let's stop there first and then see what's in here. We don't have, oh yeah, we do. We've got exactly what we want. We've got a profile directory. I got distracted by the extensions and the NB extensions stuff, which are also part of the necessity for the iProfile, the IPython parallelization capabilities that can be connected to notebooks. That's what the NB stands for. That's Jupyter Notebooks. So let's cd then into profile parallel, and we see these configuration files that were noted up here at the top when we ran the create command. We also have other helpful stuff, which are particularly directories like log, PID, security, and startup. We're not going to go into all of the nitty-gritty details of every one of these things and all of the exhaustive capabilities that exist, because this is just a demo. We don't want to spend 5 days doing this kind of thing. But we'll just start by having a look at these files that were created. The things that are interesting here is that we've got from IPython and from IPyParallel some engines, some other components that allow us to do all of this parallel and distributed computational work from Jupyter Notebook. So you have a concept known as IP cluster, you have a component known as IP controller, and you have a component known as IP engine. And these are the main three that we have to worry about. These other two are certainly significant, and there are circumstances where you would need to manipulate those. But in all seriousness, for this very simple demonstration, I don't have to do anything more with these. The act of creating them is enough with their default values that we can now use the notebook and simple parallel computational capabilities on the head node without any further configuration. So having done that, then let's go back to the web page and use this new engine, this new IPyParallel configuration to do something with our notebook in a simplistic way. So here we are back in the web user interface, and we've got a changed condition. Remember that in an earlier part of this exercise, we double-clicked on this local parallel demo notebook. And as a result of doing that, not only did we get this new tab that loaded that notebook for us, but we've changed the icon here. And this now is noted as green, and it means that it's running. We have a running notebook. We have another way of looking at it being running by looking over here in this end part of the field. It says that it's running. Another thing that's interesting to see the status of it being in the running state is if we were to come over here to this running tab and click on it, now we can see a list of all of the notebooks that are running. We don't have any terminals running, but at least we have a notebook running. We know that it's a Python 3 notebook, and we can shut it down by clicking on this if we wanted to. Now back to this concept of having a profile that allows us to run parallelization of a workload. Let's click now again on this IPython clusters tab. When we were going through the tour earlier, this was empty. When we clicked on it, we got nothing. And when we click on it now, it's also nothing. But let's click here on this refresh tab now, and we now have some engines, some cluster profiles. The IPython mechanism created for us this default one, and you saw that directory. We didn't look at anything in it, but when we were going through looking for this parallel profile, we saw a directory called profile_default. So we have that as well. The one that we created was this parallel one. What we need to do to start using it is to click on this start button, and when we do, it changes the state to running, and it tells us the number of engines that are running on it. Okay, we now have the ability to use IPyParallel with IPython as a parallelization engine back on the head node in our HPC cluster for use with our parallel demo here. Okay, now I've clicked on the tab that's got the parallel demo, and it's got a bunch of instructions, some data science instructions. I'm going to start here by clicking on kernel, and I'm going to reset everything. I'm going to restart and clear all of the output. That's just going to give us a fresh start to this notebook. Now we've got all of the output gone. We've started again here from scratch. And we have as a comment here a reminder that we need to start up that cluster engine in the background. In this particular example, I called the profile Direct View. Now I called it Direct View because I stole this example from another very kind and smart gentleman who does this sort of thing, and he does it much better than I do. And this was an example that he had, and he called his profile the Direct View profile. We're going to now instead call our example Parallel, and that's the profile that we created. And we don't need to start this because we started it back here on the home page in this IPython clusters tab. So this was just a reminder that we need to make sure that we have that cluster engine running. The next instruction that we have here is this one, and we again need to change that to parallel so that we're going to start up the right engine. Now again, there's a lot more to this. If you were a data scientist, you would just go crazy with this kind of stuff. This is just a very simple example. The way that you execute each of these cells is to press Control Enter. So I'm going to do that. I'm going to go ahead and press Control Enter, and it will execute the code. Now, it very quickly switched this little box here to an asterisk, which meant that it was executing, and then when it has completed, it gives you a numeral that tells you the order in which it has been executed. This was the first thing we executed. This is the first completed cell, so it's got a 1. We'll press the down arrow key, and we'll do the same thing on this. Press Control Enter. What this instruction does is tells us how many engines are running. Remember that we had 2 engines running, and indeed it's telling us that it's got engine 1 and engine 2. So it's just got 2 processes that are running as part of this the cluster engine that's running back here, indicated in this cluster, the IPython clusters that are running. Come back here to our demo tab. Next, we're going to create an object that's our work object that's going to use both of the engines that we have running, 0 and 1. So we'll press Control Enter. That's run and completed. And now we want to do a computation. This is data scientist speak here. We're going to create this lambda function that's going to do this mathematical computation and then run this range function to the tune of 30, and it should give us some result. What this is going to do, though, is run the functions serially. We're just running a list function one time, giving it to the head node to compute, and then giving us the data back. So press Control Enter, and it's going to give us some interesting information about what happened for that serial computation that took place. In the next one, we're going to do the same thing, but this time we're going to use that dview object that we created, that we're using those engine objects, those back-end cluster engines, to parallelize the computation. We're going to do the exact same computation, you see that right there, but we're going to now pass it to run parallel amongst 2 different computational engines. So I press Enter, and it's done very quickly. At this time, it took a little longer in terms of CPU time, right? You see that it originally took 20 microseconds, and here it took 10 milliseconds, but the wall wait time was also longer. And that's because you have a little bit of overhead associated with parallelizing this. When we did it just all once, singularly, it was pretty quick. That's only because of the simplicity of the computation that's taking place with the added overhead of parallelizing it. When things get more difficult, more computationally significant, then you'll eventually see a turnaround of those details. All right, so let's run the next cell. This tells us we created a function called getPID. This is telling us what the process IDs are of those engines that are running. Then we're going to use a standard computational science tool called NumPy. It's just a bunch of number calculation tools that exist. And we'll run this, press Control Enter, and we get, we have a problem. And that's okay. This is something that would occur normally in everyday use. We don't have a module called NumPy. We don't have the Python module installed for NumPy. Well, we can fix that, and I can do that without having to irritate the system administrators. I'm just going to install NumPy locally for myself as the scientist user. I'm going to create a new cell, and this cell needs to go up a little higher, so I just highlighted this cell, and I can move that with this button here. And here I just need to run, that bang there says run this not as a notebook command, but as a system command, pip install numpy, but I need to do it as a local user, so I qualify that with this user switch. And then I press Control Enter to run that command. It downloads it, installs it in my local environment, my scientist user environment. And now I can use that just for me. Now it's giving me an interesting warning here. Now I don't have local bin in my scientist user's path. And so for me to inherit that back again so that I can run this import here, this next cell, I have to reload my kernel, kind of like what I did before. So I'll come back up here to kernel and I'll restart the kernel. It asks me if I really want to do that because all my variables will be lost. Well, this is a very simple model here. I don't need to worry about that. So my kernel has now reloaded. I can get rid of this cell now if I wanted to, but no harm leaving it there. But I can now rerun this cell. I'm going to press Control Enter, and I have NumPy. Okay, now what's my, oh yeah, okay. I lost all of my variables. All right, so let's go back to kernel and restart and clear output again. Just start from scratch. Come back up here to the top and start again. No big deal. Control Enter, down, Control Enter, down, Control Enter. There I got my dview object back, down, Control Enter, down, Control Enter, down. Now I got to redefine my getPID, Control Enter. Now I don't need to run this one again. I already installed NumPy, so I can just press down again. And this time, let's see, I'll scroll. I'll press Control Enter. And it worked this time because I have NumPy installed. I don't get any errors. I have a numeral 7, which means it completed, and I'm happy. Now let's use that. We've now defined this new function called pmul, and I'm going to use that. I'm going to do the same thing that I did before. This time I'm going to have show this time stamp to tell how long this computation takes place. The first time I do it, I'm just going to do it by calling it serially by one processor here on the head unit. So I'll press Control Enter, and it happened that fast. I'm going to do it again now. This time it's going to call out to those engines and is going to do it in a parallel manner. Oh, I got an error. What was my mistake? What's my error here? Well, look, I don't have NumPy installed on any of the where it can be used externally. At least that's what it's telling me. And that's where you get back to the same challenge that we have that we've described earlier, that this tried to run it externally, outside of the context of my notebook. Inside the context of my notebook and of my kernel, my running environment here in Jupyter Hub, I have NumPy. But because I sent it out to be calculated externally in a parallel method outside the context of this running Jupyter Hub notebook, it doesn't have NumPy. And that's where I now need to have NumPy installed for the rest of the users in the system. Now let's see if I can trick it by coming back to this command here, and instead of using that user tag, Let's just see if I can force it to work so that everybody can use it. Now, it's only going to do it here because it thinks that it's found here. I now have to tell the system administrator to install it. So let me break away briefly and go install this on the back end and make it available for everybody. And I'll be back after a break. All right, having then communicated with the system administrators, which in this case is myself, I've got NumPy installed on the head node, and I can now just press Control Enter here, and it works just fine. Again, it's going to take a little bit longer, just because it's a small computation, right? You've just got A and B right there, but that's okay. We've got the principle, and that's what matters here. We'll do the same thing then here. Well, you've seen enough. We don't need to worry about the rest of what's going on here. This is a demonstration of just a regular notebook and what a data scientist would do with a regular notebook, but only in the context of running it directly on the head node. We're not really using any of the distributed resources of the compute nodes of HPC yet. And that comes in the next portion of the demonstration. All right, for this portion of the demonstration, we're now going to create a profile that will allow us to use MPI in the high performance computing environment. Now this gets to be far more complicated, and I apologize for this, the difficulty of doing this. This is really a function of the fact that MPI can be a little challenging, but more specifically, the kinds of complication that you're going to have in this configuration has to do with the fact that I'm doing this in the AWS environment, where I have to be very meticulous with ports. If you were to do this yourself in your own environment and you have a different kind of control over firewalls and ports, it might not be quite this difficult. Okay, with that caveat set, this is still challenging for a data scientist because you have to modify these files in a very particular way with knowledge of how MPI works and of how of what's going on with the HPC configuration. We're going to start by doing a very similar thing that we did before. We have to create a profile, and we'll do that from the command line again with IPython profile create, and again we'll call it make sure that we know that it's got parallel capabilities. We're going to add a particular detail here about where the profile directory is going to be stored. It's from the home directory .ipython/profile-mpi. And then the name of the profile is, again, going to be MPI. It's a little bit redundant, but trust me, it's meaningful and makes a difference. I'll press the Enter key, and it's going to do the same things that it did before when we created the parallel profile. It's now going to store it in this profile MPI directory. So let's cd into that directory. Yeah, we're right here, IPython profile-mpi, and see exactly what we saw before. Now we need to modify some of these files to make this work. We'll just start at the top and go down. I'm going to use the VI editor. You can use whatever editor that you want. I'll just take for granted that you understand what it is that I'm doing here, and try not to be overly complicated. So I'm going to VI IP cluster config.py. We looked at this as an example earlier when we were looking at it from the profile parallel perspective. Now we need to make a few minor adjustments. We could make a lot of adjustments depending on what it is that we want to do. It's very, very sophisticated in the kinds of things that could be modified. But we'd only need to modify a few things in this file. So let me scroll down a little bit and see if I'm at the right place yet. No, let me scroll down a little bit more and see if there's anything else I need to change here. No, I don't. Notice here that it has created values for these things. If I wanted to use to customize these settings. It's already outfitted them with values that are specific to my environment. That's really cool and helpful. But it's commented out. You can see over here on the left, it's a commented variable. I don't need to change that. Let's see, what else do I need to change? I'll scroll down another page. Here it is. We're in the range where we need to start paying attention. You see that we've got some comments. This is all documentation here. That the IPython's bundled examples of launchers include these categories: MPI, PBS, all these others. And also Slurm down here, one of my favorites. And that's the sort of thing that we need to change here. We'll come down to this section right here and change this value to, we'll remove the comment and change this value to the end of that quotation mark. We want that to be MPI because that's what we're using. We're using MPI. Good. I'll then get out of edit mode there, and I want to also change this one. The default value for the number of engines is 2, and we'll change this to 4. We have 4 nodes, 4 compute nodes. I'm just going to change that to a value of 4. Let's see, the next thing we need to do, whoops, sorry about that, and I scroll down a little bit more. Got to find where we need to change it. We'll want to change this one as well. This is the controller launcher class. I'll go to the beginning of the line and remove that comment and also change this to MPI. The last thing that we need to do, it's called args, something args. There we go. It's the MPI launcher args. I have to change this to tell it to make it aware of the hosts that I'm going to be using as compute engines in my cluster. So I need to change that to, I think the syntax goes like this. I probably need to put a dash in front of it. Host, comma, and then the values are AIML HPC. Do you remember when we did this in the HPC and in the MPI example, when we were doing an MPI running of the CPy file? We have to do the same thing here. We're going to pass it this comma delimited list of all of the hosts that will be hosting an engine, an IP engine in my cluster. AIML HPC-C3, comma, AIML HPC-C4. Close out with a quote. Okay, I think I've got that syntax right. Is that right? Yes. Okay, I'll exit out of edit mode, and then this is all I need to change here. Note that the execution for MPI is going to be using the MPI exec, and we would expect that. And we don't need to change that because that's the default value, the default behavior. All right, I will write and save this file and exit out of it, and that's the first change we need to make. The next file that we need to change is the IP controller. Good, we'll edit that file. We could change a lot more than we have here, but we don't need to change everything. The first thing that we do need to change, though, is to change the behavior of who it is going to listen to. Notice, here's another one of those things that it has customized our configuration for our environment. I don't need to uncomment this out because it's the default behavior is going to be appropriate for this, but it's interesting that it's written the file that way. Where is the setting that I need? I'm trying to remember what it's called. I know I'm getting warm here. Where am I? It's got to be, it's called client IP. There it is right there. Okay. So I need to change this, and this is uncommented, and I need to give it a format that will allow it to listen to anything in my cluster, anything on this network. I could be more meticulous in how I change this. So if I'm in a more wide open network, I'm worried about other things connecting to my hub, to my Jupyter hub, I don't care about that in this case, because I know that in my environment I've only got my cluster head and the compute node. So I'm going to open it up wide open with this syntax. Then I need to start defining ports. This is the part that is ugly for my AWS environment. I have to change this, and there are a lot of them, to the controller, to being, notice that it's a pair, and I have opened up a certain set of ports for this to work. So we're going to start at that one and go with one there. That looks right. And then the next set of ports I need to change are this one. We'll change this to a pair, and 1000, the 2, 10003, and then this is a pair, 10004, 10005, and I think I need to change that one too. Let's see if I have to change that one. The mon port, yeah, I do. So we'll change that to, let's see, did I miss one? Let's see. I think I'm worried that I started this at the wrong number. Let's be sure I'm not messing this up, because I don't want to mess this up and have to go back and redo the recording and everything. Get that to there, and then change this to a 3 and a 4. Change you to a 5 and a 6. And now, yeah, this is looking more like it. You're a 7. Whoops, too many zeros. 7. Good. Oh, I have to uncomment that, and I need to uncomment that. Yeah, that would have been tragic. Then I think I need to change the monitor IP as well. No, I don't need to change that one. No, that one's safe. But now I do need to change the mux. There it is. And we left off at 7, and we need a pair here, 1008 and 9. And then I do need the notifier port. That's going to be, that's correct, and comment that. And I don't need to change, maybe I need to change the timeout. I'm doubting the timeout. I'm going to leave that one alone for now. But then I do need to change this and add a pair. 10011, 10012. Okay, that should be it. Okay. Those are all of the changes that I need to make. And again, this is simply because I have to accommodate my contrived environment in Amazon. The only thing I really had to change was the listening to the, look for client IP again. Client IP. There. This thing. For you, likely you only need to change that. Let's hope that that's the case for you. Having done that, I will write and quit, and we're good with that file. All right. Now, I think the last thing we have to change is this IP engine file. We'll go ahead and edit that. And this thing that needs to be added in this file, of course, we could do a whole bunch of other configuration changes, but the thing that really needs to be changed here is one that is an additional variable that doesn't exist yet. And I'm just going to find a good place for it. I'm trying to think where the best place for it is. Probably not there. Let's look for something that says MPI. Yeah, this is a good spot for it. Yeah, we need to use, as a matter of fact, it makes reference to it here in this comment. We need to use a facility called MPI4PY. And this is kind of a mean and dirty trick that we play on you. But in order to use a go-between with the Python engine and the IP engine, which is native C, and MPI is native C, you have to have an API go-between. And that's this for MPI thing. We're going to add a line here, and I think it's C dot, what is it called? MPI.use equals, yeah, that's right, MPI for PY. So there's a package called MPI for PY that needs to be installed on your engines, on your compute nodes. Don't need to worry about installing it on the head node, but the compute nodes will have to have it. And then I think that's the only change we need to make in this file. We'll write and quit. I'm pretty sure that's all we need to do for the creation of the profile data. Now there's still more that needs to be done to get these, to make use of these profiles, but that comes here in the next step. This next step is pretty technically sophisticated, and it's an unfortunate detail of what needs to happen from an HPC perspective, and from both an HPC perspective and from an IPY parallel perspective, from an IPython perspective. To be able to make use of the compute nodes in our distributed computational model, we have to run an engine on each of the compute nodes. We have to run an IPython engine. It's called an IPython, it's actually, that is what it's called. It's an IP engine. It's an IPython engine, or an IPython parallel engine. The IP engine process needs to run on each of the compute nodes. Now there are certainly a variety of ways that you can do this, and again, it's the kind of thing that needs to be implemented in a different way to make this easier for your typical data scientist to be able to accomplish. That sort of easier way doesn't exist yet, and that's the sort of thing that we're trying to improve upon as we create a better solution from a SUSE perspective. But the easiest way that I have found to do this is to take advantage of the fact that the scientist user has this NFS distributed home directory all throughout all of the hosts in the cluster. So we could just install this IP engine stuff in our home directory so that it then can be run on each of the different compute nodes. To install the software on for the scientist, that is the IP engine software, we're going to use Python to install it here in our local, in our home directory. Now, of course, we could ask the system administrator to install this IP engine software for us so that it would be available on all of the different compute engines. But we'd just as soon be able to, as the data scientists, to take the matters into our own hands and control our own future with these tools. These are specific tools for what it is that we're doing for our environment, for our calculations, for our data analysis. We should be able to have that kind of control without having to bother the sysadmins. And so we will, and we can. Now notice here on the screen we still have the bash terminal, but I've changed things up a little bit. I've created a screen session, and I've got 4 different screens running. Don't let that distract you too much yet. I'll come back to this in a moment. For now, to install the software that we need to run as an unprivileged user, as the scientist user, I just need to be logged into the head node as my unprivileged user named scientist. And I'm going to use pip to install the IPY parallel software here into my local home directory. When I say local, that's probably not the right way to say that. In my NFS home directory, When I said local, I was just talking about the fact that it is mine. It doesn't belong to anybody else, but I can just say home to mean that. So all of the stuff that gets installed by Python that's going to be just for me as a user gets installed into this local directory. And there's already stuff there. Remember, we installed NumPy in an earlier exercise, part of this demonstration. So that's already here, but we just need to install IPY parallel. And to do that, we'll run pip install, and let's see, I'm trying to remember exactly the syntax I have to use for this. We'll go ahead and install it as user, and because IPY parallel is already installed at a system level for everybody by the system administrator on head, I have to reinstall it. I have to force install this, and that just means I have to use an extra switch to tell it to ignore the fact that there's a system version of this, but also install a copy of it here in .local for me as the user, from a user perspective. So let's see if I can just remember how this goes. Pip install, yeah, that's right. It's the -I argument that will force a reinstall, and will, by virtue of my using the --user, is going to install it here locally and forget about the global installation of it. All right, I'll press enter here and hope this works. Good, it looks like it's working. It's downloading IPY parallel from the internet and installing those packages, all of its dependencies. You see the list of the dependencies there at the bottom. And good. Now it's giving me some warnings because I'm installing this new here in my environment. It needs to be able to add path elements to my path. And unless I re-log in, I won't pick up that information. I don't really care about that on the head node because I'm not going to be rerunning this stuff on the head node. The purpose of my installing this into the .local directory on my NFS home mount is that it's going to be available to all of my home directory. It's going to be available to the scientist user on all of the compute nodes, like compute 2 and compute 3 and compute 4. And I haven't logged into those yet. When I log into those next time, it's going to then add that local bin to my path. So I should be okay without having to re-log in here on the head node. Having done that, I now need to go through the process of running the IP Engine software that came with this stuff that I just installed on each of the distributed, the remote compute nodes, compute 1, compute 2, compute 3, and compute 4. And to do that, I have to shell into them, logging in with I've got my SSH auth key, so I don't need to actually log in. I mean, I need to shell over there and be authenticated with my auth keys. And then start up the IP Engine on each of them. If I'm going to be running this on 100 nodes, that's really tedious. For this demonstration, I'm just using 4. And again, I'm recognizing that that's kind of a pain and something that we need to solve, and we're working on that kind of thing. But the scientist user needs to run her own IP Engine on each of the compute nodes. So here on this first shell screen, I'm going to do exactly that. I will SSH to AIML HPC-C1. And I've got my auth keys there. And you'll see now, because it's NFS and my home directory, I have .local. And in .local, I've got exactly what I installed from my head node. And in here, I've got exactly the stuff that I installed, including all of the supporting software related to IPY parallel. And this is the main one that we need to use. Now, it would be convenient if I could just run IP Engine just by itself and not worry about anything else, but I have to qualify it. I have to, because it's not in my path, right? I guess I should have hoped that that was going to be in my path. Yeah, why isn't it in my path? That's another good question. But even so, it's not terribly important that I fix that at the moment, because I can certainly call it by fully qualifying its location. And it would still be nice if I could just run .local bin IP engine. If I could just do that and have it figure out what's supposed to happen, that would be great. And it is going to run an IP engine, but it's not running the right one. It's got the profile default. And so that's not going to help me, and it ends up crashing because it doesn't have any of the server side stuff running to make it meaningful yet. What's really nice though is that you remember I've got this profile that I've created, and it's also in my distributed NFS home directory. So I'm going to go into IPython. How do I spell that? And you remember I've got my profiles here, including profile MPI, and I have in here all of the stuff that represents the configuration, the profile that I have for what I want to be running from my Jupyter Hub as the means of communicating with the IP engines that I'm going to start up. And when I start the cluster service in Jupyter Hub, it's going to provide for me the connection information, the API, if you will, where that these IP engines can start up. And that information is going to be contained in this security directory. So I'm going to stop here and go back to the Jupyter Hub web page and show you there that we need to start up the Jupyter Hub side portion of the engines so that these compute side engines can connect with it. Here in this portion of the demo, I have come back to the Jupyter Hub web page, and I'm logged in as the scientist user. And what I need to do now is to start up the Jupyter Hub side portion of the engine that's going to allow us to do a distributed computation. And you'll see here I'm on the standard files portion of my Jupyter notebook here, and of the Jupyter Hub. And I've got notebooks here available to me. I've got the one that I started earlier, the local parallel demo, which didn't need all of this extra configuration to allow computation to take place on the remote compute nodes. What I want to end up doing is run this guy right here, this MPI demo. You'll see that it's not currently running. It doesn't have that green icon like the local parallel demo does. So let's go ahead and just double click on that and start it up. And let's see what's going on here. Sorry about that. I had done something unexpected as I was dabbling with this overnight before beginning the recordings this morning. I had mistakenly broken something, but I've just now fixed that. So I should be able to now double click on this. There we go. Actually, I didn't even have to double click. I can just single click. All right, now that my Jupyter Hub server is working correctly again, we can load the notebook. And here I have, this is the exact same demo that we have from the local parallel demo. It's got the same instructions, but in this particular one, we're going to connect to the profile MPI. Now I can't connect to that profile MPI until I've come back here to Jupyter Hub and I come to this IPython clusters, and I need to start this engine right here. See that it is stopped. I'm going to come over here and click start. And this time, because I configured it, you remember I changed those those variables in the IP cluster configuration file to have 4 engines running, because I've got 4 compute nodes. I'm going to make sure that I have those 4 engines running, and indeed they are. So now I have running from the Jupyter Hub side the means to connect those engines. So I'm going to stop the interaction here with the web UI of connecting to Jupyter Hub and go back to the command line of bash and now set up those IP engines on the compute nodes. We've switched back now to the command line where I have that session of screen running and connected to the 4 different compute nodes. Right now I'm connected to the compute node 1, and I'm connected as scientist, and I'm currently looking at this profile MPI directory. And having gone in the previous step into Jupyter Hub and started the cluster service from the Jupyter Hub side, I now have a process that's running there from Jupyter Hub that has created 2 different JSON files in this security directory. And you've got the client side, which is the Jupyter Hub side configuration, and you've got the compute node side, which is this engine JSON file. And this has all of the information that is needed to be able to connect the one to the other. So I'm going to, just for convenience, I'm going to cd into the security directory. And, well, I don't need to less it because it's a short file. I will cat it, and we'll see IP controller client. And so from the Jupyter Hub side, you are serving all of the different APIs using this set of ports. And you hope you remember that we had to configure those ports with the configuration file on the head node. If I hadn't made these specific port assignments, then the Jupyter Hub would have started up this IP controller and would have randomly assigned ports, which under most normal circumstances would have been fine. Because I am in AWS, I have a very a controlled security group. I didn't want to open up all ports because of AWS and getting hacked. So I very meticulously configured my configuration file to open up these specific ports within a range that I did open up in the AWS security group. So this is the client side. This is the Jupyter Hub side configuration file. Now we look at the IP controller engine, which is now going to be the compute node side of the configuration. And some of these are the same, right? The registration port is going to be common between them, but on the server side, the client side, the Jupyter Hub side, you've got the control port, which is port 1 here, and then on the engine side, you've got port 2, so the forward and backward communication that's going to take place. And similar for all of those different pairs that we had to set up. So at least I have the means whereby the engine on the compute nodes can communicate with the client on the Jupyter Hub head node. Excellent. With this set of information, I can now run IP engine to start up and to connect the engine to the Jupyter Hub controller that I have running. So I'm going to use the fully qualified, oops, what did I do? The fully qualified path here, .local and bin IP engine. And then I have to give it a file designation that contains all of this information. And again, I'll use that fully qualified path. And this time it's going to be IPython. And why is that not completing? Oh, I can't do tab completion because of the stupid way that the interpreter here this is an argument with an equal sign, and so that interrupts my ability to do tab completion. Sorry about that. So we'll just do profile MPI, security, and then the name of the file. And this is the engine, IP controller, controller dash engine.json. Now when I run the IP engine, it should be able to not only find something listening, it does a completed registration with ID 0, and it's connected to the Jupyter Hub. Super. I have to do this 3 more times. Now in the past, I said, oh, I'll just let you do this on your own on each of the compute nodes. I think this is important enough here that I'm going to show you how to do this on each of them. It's going to be the exact same command line for each of them. So I just switch now to the compute 2. I haven't logged in yet, so let's do that. AIML HPC compute 2. So there we are connected to 2. And because this is my NFS home directory, I can run exactly the same command. I've got the exact same software installed in my .local directory, and I've got the IPython profile shared. What a benefit that this shared file system is using NFS. I'll run this one, and within a moment it should come back and tell us that it has registered as 1. Well, let's hope it tells us that. Wait a moment. Well, it failed. Let's see if I can figure that out. I'm going to pause the recording. Oh, there's a really simple explanation for this. Look, engine is misspelled, and that's just because it wrapped off the screen when I did the copy and paste. So if I'm going to fix this, I just have to go up to recall the command and add the N here so that it's going to refer to the file. That character just got cut off in the cutting. There we go. Now it's completed registration with ID 1. I just need to do the exact same thing on the next 2 nodes. Here we go. Switching to compute 3, SSH AIML HPC-C3. Run the exact same command here. It's not cut off this time because I copied from a portion of the screen that didn't wrap, and should be able to run. And there we go. We've got the next engine ID is 2, and then we'll switch to compute 4, shell into AIML HPC-compute 4, and run the same command here. Oops, well, that was dumb. I have to go back because I highlighted that 2. I lost it out of my buffer. So now we've got to highlight this and go back here to 4 and run it here on 4. And that should come and tell us that it is now registered with ID 3. I've got 4 engines running, 0 through 3. Now I'm perfectly set up to be able to hand work from my notebook in Jupyter Hub off to these 4 engines to do computations. Back here at the Jupyter Hub web UI, I'm at the main screen for my scientist user, and I have the local parallel demo running. It's got the green icon and it says that it's running. And I have the MPI demo that's running. Now I could just click on this again, but I already have the tab for that over here, so I'll click on the tab. And here we are with the notebook. We've started the cluster engines, and now it's just a matter of starting up through this process of each of the steps in the notebook that we have here. Again, this is the exact same set of instructions that was in our local parallel demo, but in this particular notebook, we're going to connect not to the parallel profile, we're going to connect to the MPI profile, the profile that allows us to connect this notebook to the 4 compute nodes that are running IP Engine. In this notebook 2, which is different than the local parallel demo, I have added more helpful data, more direction, more instruction, more just notes to accompany what it is that's happening here. Ideally, I would do the same thing with the local parallel demo. What's really, I think, necessary at this point is for me to acknowledge that I didn't write any of this data science in this notebook. I am not a data scientist. I borrowed this from a good man by the name of Dan van Hoijmeren. I suspect that that's a Belgian name, perhaps, or someone from the Netherlands. I don't know. But he is a lot smarter than I am, and he has this parallel tutorial that helped me to understand how IPY parallel works. I have adapted all of his good work to make sure that it works for this HPC demonstration. So some of this is my own work, but it is based entirely on the excellent work of that user. So in the first step, same as before, only this time using MPI. I'm going to press enter there, control enter, and you'll now see that it's connecting to 4 engines. And that's the 4 HPC IP engines that are running on the compute nodes. And here I will assign an object that will use all 4 of those engines. And as we did before with the local example, I'm going to do a serial computation using those engines. This time I'm going to do a parallel computation using those engines. Now it's taking a little while longer because it has to go, I'm sorry, let me go back. I said a serial computation. In the serial computation here, I'm not asking the 4 HPC engines to do anything. This is just a list computation that's happening right here on the head node. That's why it's so fast and came back so quickly. Just because it was serial didn't mean that I was sending it out serially to the 4 distributed computational nodes. It's simply that I was doing something that was just run locally on the head node using the Python list command local to the head node. When I ran this one, though, remember I did pass this to the V object, which is the 4 nodes in the distributed mechanism. And when that ran, yeah, it took a lot longer. When I ran it just local on the head node, it only took 25 microseconds. When I sent it out, broke out the job out to 4 compute nodes, I have the overhead of assigning that out there, getting passed over TCP, the engines doing whatever it is that they need to do with it. They're doing the computation and assembling the information and passing it back, all that. So it took 2.25 wall seconds, a little bit longer. That's okay. It's a really simple computation of just a list with just this x22 and this range function. Not very complicated. If I get a lot more complicated computations, then I get the payoff of distributing the work out to those HPC nodes. What's most important to recognize, though, even though we might not like it, is what's central to this demonstration is I sent this work to the 4 nodes, had the 4 nodes do the work, and got the information back. That's monumental. All right, we'll do this next command here. Now we're going to go through an exercise of how we use remote function decorators, and it's the exact same thing that we did in the local parallel demo. We're going to go ahead and assign a new, define a new function called getPID, just like we did before. And when we run it this time, we're going to show that these are the different PIDs for those 4 engines, for the IP engine process that's running on those 4 separate compute nodes. These aren't process IDs of the local engines. This is the this is the process ID for the remote IP PIDs. All right, let's import NumPy again, and that succeeded. And we've gone ahead and assigned A to be a function that comes from NumPy. And now we're going to define a new function called pmol that uses that A function that we just assigned, well, symbol, that variable that we just assigned. We'll run that. And now we're going to run that same thing locally. This is only going to run on our head node, so it's going to be really quick, just under a millisecond. And then we're going to do this remotely. We're going to send this out to the compute nodes, and that was pretty fast. Even though it's certainly slower than just running something here local, this came back in 17 milliseconds, which was pretty darn fast. Okay, and now let's do this here, define a new function called echo, and all that's going to do is tell us what echo, going to send back what is being sent. In this case, this is going to happen to a virtual object. In other words, we're sending this out to each of the compute nodes, and we're doing it in a parallel way, and we're going to block true here, meaning don't go on until we get everything back. So the first time we run this is really fast, and then we're going to do that there. So it's a fast function here, but is demonstrating here this block equals true. It says don't return until you've got everything completed from each of the remote nodes. And here's some more about blocking. We'll show some function names here that exist out on those remote nodes. Show us every function that begins with apply, and there are 3 of them. And so we're going to do this applying of this lambda function, and we get back the computation of 42, which is 5 plus 10 is 15 plus 27 is 42. So we're pretty happy that each of the compute nodes is correctly doing arithmetic. Yeah, that's really exciting. This time we do block equals false, and we still get back the same computation. We'll do similar things with those values that we defined up here in this step here, and do a remote execution on just node 2, and we'll do this on computation on 1 and 2, and then we'll see what the values are that we get back. On the first guys, we got a plus b, and on this one we got a minus b. So for non-blocking execution, we've got a new function that we're defining called wait. And here we will assign the variable AR to that wait. And it took a very short amount of time to, of course we're just defining AR. Now we just need to tell it to get. And all it's going to do is wait for 3 seconds. So go ahead and count with me. Oh, why did it only take, that was very fast. I'm not sure why that didn't work the way it's supposed to. Let's try this one here. This is supposed to be waiting 10 seconds, and that happened really fast. Oh, I know why. That's dumb. Okay, I'm going to keep running this. Let me explain to you after. See that it says false. I'm going to run it again. True. So what's happening here is, knowing that this is supposed to wait 3 seconds, we've got some computation here in terms of the approximations of how many is 3 for 3 seconds, and that's pretty close to 3 seconds, you see there. This time when we do wait for 10 seconds, if we do it fast enough, then we'll see that it is supposed to end up being false, because it's waiting for that to take place before it then turns to true. So we'll do that again. Let's run this one again. And when we quickly run this, it will be false, 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 false. Pretty soon it's going to be true. There, it's true. That's a demonstration of how blocking works. And then this is just showing that it's supposed to wait for 10 seconds. Another example here. I'm not sure any of this is helpful to you anymore. This notebook is kind of cool though, because it's got all these examples of how this stuff works. You've had now demonstrated in a fairly definitive way that I'm able to connect to this MPI engine, which connects to the MPI mechanism of HPC, which is able to distribute work to the distributed remote compute nodes in my HPC cluster. And that's pretty significant, and that's really, really helpful for a data scientist. Moreover, we've got the opportunity here to abstract away some of the responsibilities that the data scientist can do by himself without having to persistently pester the DevOps folks, any of the system administrators who are responsible for managing the infrastructure. So this is a good way of bringing these two functions closer together, facilitating good data science and using the benefit of high performance computing environment. And with that, we've accomplished what we set out to accomplish, not only for this section of the demo, but for the entirety of the demo itself. In this last step, we set up a standard user called Scientist. As the Scientist user, we ran the Jupyter Notebook, and as the Scientist user, we were able to, oh, I spelled Jupyter there. That's terrible. Sorry about that. As a data scientist, we were able to run the Jupyter Notebook and take advantage of the high performance computing compute nodes using MPI in the cluster. This is a great step in bringing together, in further marrying the AI and ML aspects of data science with the needs of a system administrator or a DevOps organization that's trying to provide the infrastructure and the compute capabilities to these data scientists, as well as many others in an organization. This is a great marriage, and this is a great step forward. We look forward to further developing this set of tools and this infrastructure that anyone who participates with SUSE can take advantage of, and really see the power of what's behind high performance computing and AI and ML together.